We've dreamed of living on Mars, but recent research proves it's a death trap for humans. Here's why. What survive actually means in science. When people hear humans on Mars, most of them picture the same thing. A spacecraft landing in red dust, astronauts stepping down a ladder, a flag in the soil, a habitat glowing under a pale sky. Those images are powerful, but they are not scientific. They do not answer the only question that actually matters. Not whether humans can reach Mars, but whether humans can remain there in a way that biology recognizes as survival. In science, words are not flexible. They are precise, because nature is precise. A planet does not care about optimism, ambition, or how impressive a mission looks on video. It only responds to physical laws and biological limits. That is why, before scientists ever debate radiation, gravity, food systems, or technology, they start with definitions. If the definition is wrong, every conclusion built on it will be wrong too. So when scientists talk about survival, they are not talking about landing a spacecraft. Landing is an engineering challenge. It involves propulsion, navigation, materials, and guidance systems. Those problems are already solved. We have landed robotic laboratories on Mars multiple times in multiple locations with increasing precision. The act of landing proves that humans can calculate trajectories and control machines across interplanetary distances. It proves nothing about whether the human body can exist in that environment over time. Survival also does not mean staying alive for a few months or even a few years. Human biology is capable of enduring extreme conditions temporarily. People survive months in Antarctic research stations, years aboard submarines, and long-duration missions on the International Space Station. In all of these cases, survival is conditional and temporary. The environment is hostile, but the exposure is limited. When damage accumulates, people return to Earth. Mars removes that escape. A condition that is survivable for 6 months can become lethal over decades, especially when the damage compounds rather than stabilizes. Because of this, space agencies and medical researchers use a stricter definition. Survival means that a population can persist without collapsing. That requires 3 core criteria: long-term reproduction, multi-generational health, and independence from continuous resupply from Earth. If even one of these fails, the environment is classified as non-survivable for humans, regardless of how long individuals can endure it. The first requirement is long-term reproduction, and it is not negotiable. For a human population to survive, it must be able to reproduce safely and reliably over time. That includes healthy sperm production, healthy egg development, normal fertilization, normal pregnancy, and normal fetal growth. It also includes successful birth outcomes and healthy childhood development. If any stage of this process is consistently compromised by the environment, the population is not surviving. It is merely delaying its disappearance. This is not theoretical. It is the same standard applied to wildlife populations on Earth. A species that can survive as adults but cannot reproduce in an environment is considered non-viable there. The same logic applies to humans. One generation living out their lives on Mars would not count as survival. Survival requires that children can be born there and grow into healthy adults who can then reproduce again. The second requirement is multi-generational health, and this is where environments often fail even when reproduction technically occurs. It is not enough for children to be born alive. Their organs must develop correctly. Their bones must mineralize normally. Their nervous systems must mature without chronic damage. Their immune systems must function effectively. If health declines with each generation, the environment is exerting a biological pressure that cannot be adapted away. Multi-generational health is one of the hardest criteria to meet because biological damage is often subtle at first. Small increases in mutation rates, slight impairments in organ development, or chronic low-level stress on the body can appear manageable in one generation and catastrophic in the next. Scientists look for stability. If health outcomes degrade over time, survival is already failing, even if it takes decades to become obvious. The third requirement is independence from continuous Earth resupply, and this rule eliminates most popular visions of Mars colonization immediately. Survival means autonomy. Food must be produced locally in sufficient quantity and nutritional quality. Water must be recycled without irreversible losses. Medical systems must operate without relying on Earth-based hospitals, constant pharmaceutical shipments, or emergency evacuations. Infrastructure must be maintainable using local resources or closed-loop systems. If the population collapses the moment Earth stops sending supplies, it is not surviving. It is being supported. This distinction matters because many proposed Mars settlements are functionally dependent on Earth in ways that cannot scale or persist. Continuous resupply is feasible for missions. It is not feasible for survival. Rockets are expensive, slow, and vulnerable to failure. A population that requires constant shipments from another planet is not independent in any biological or ecological sense. These criteria are not controversial. They are standard. They are used in population biology, closed system research, and long-term habitat studies. They are the same rules applied to isolated environments on Earth, such as remote islands or sealed ecological experiments. Mars does not get an exception simply because it is difficult or exciting. This is where public discussions often go wrong. The word survive gets replaced with softer ideas like live, stay, or endure. Those words allow for temporary success to be mistaken for long-term viability. A mission that lasts 2 years can be described as humans living on Mars. But that does not mean Mars can support human life in a lasting way. Science does not blur that line. Space agencies are careful about this distinction internally, even when public messaging sounds optimistic. Mission success, crew safety, and long-term biological viability are treated as separate categories. A mission can be considered successful even if it exposes astronauts to risks that would be unacceptable in a permanent settlement. Astronauts are informed adults who accept damage to their bodies as part of their profession. That does not make the environment safe. It only makes the risk voluntary. Astronaut health data is often misunderstood for the reason. Astronauts are not evidence that humans can survive in hostile environments indefinitely. They are evidence that humans can tolerate damage for limited periods. Bone density loss, muscle atrophy, vision impairment, immune dysfunction, and radiation exposure are all documented consequences of long-duration spaceflight. These effects do not disappear because astronauts return to Earth. Some reverse partially, others do not. Mars would remove the option to stop the exposure. The scientific question then is extremely narrow and extremely strict, not whether humans can travel to Mars, not whether humans can build shelters there, not whether humans can survive for a year or two under carefully controlled conditions. The question is whether humans can remain on Mars, reproduce there, raise healthy children there, and maintain their population over multiple generations. without depending on Earth to keep them alive? Once that question is asked correctly, the analysis changes completely. Temporary success becomes irrelevant. Short-term endurance becomes meaningless. The environment must support the full biological cycle of human life, repeatedly, under constant exposure to Martian conditions. This is why scientists insist on defining survival before discussing solutions. Without the definition, every debate becomes confused. With it, the data can be evaluated honestly. Mars is not being judged against dreams or intentions. It is being judged against human biology as it actually exists. With these rules in place, Mars is no longer a blank canvas. It becomes a test environment. Its gravity, radiation levels, atmosphere, soil chemistry, and resource availability are measured against the requirements of human survival. There is no room for interpretation. Either the environment meets those requirements or it does not. And once the rules are set, they do not change later to accommodate hope. They remain fixed while the evidence accumulates. This is the foundation. Everything that follows builds on it. Why temporary missions do not equal survivability. Once survival is defined correctly, a second mistake becomes impossible to ignore. Temporary human missions to Mars are often treated as proof of progress toward permanence, as if time alone can turn endurance into stability. In science, duration does not automatically translate into viability. An environment that can sustain human life for months or even years can still be fundamentally incompatible with long-term biological survival. Mars fits this pattern precisely. Temporary missions are designed around tolerance, not sustainability. Every system is built with an expiration date in mind. Life support hardware is optimized to last just long enough. Medical risk models assume that accumulated damage will be treated later on Earth. Nutrition plans are based on stored or partially recycled supplies. These are rational choices for exploration, but they conceal the true behavior of the environment over longer timescales. When scientists analyze survivability, they remove the safety net of return and resupply. What remains is the raw interaction between the human body and Mars. Radiation exposure is the clearest example of this difference. Short missions accept radiation as a calculated risk. Limits are defined based on career exposure, not lifetime exposure in a fixed location. Mars continuously bombards the surface with high-energy cosmic rays and solar particles because it lacks a global magnetic field and a dense atmosphere. During a temporary mission, exposure is measured, recorded, and tolerated. Over decades, that same exposure becomes cumulative and irreversible. DNA damage does not reset. Cancer probability does not plateau. Neural tissue does not regenerate. A mission can end before the most severe effects appear. Survivability cannot rely on that timing. Gravity introduces a similar problem. Partial gravity on Mars is often described as an improvement over microgravity. But survivability depends on thresholds, not comparisons. Human physiology evolved under one gravity value. Bone remodeling, muscle maintenance, cardiovascular function, and fluid distribution are all tuned to that constant load. Temporary exposure to reduced gravity produces degradation that is considered acceptable only because it can be reversed after return. Long-term exposure removes that assumption. If bone loss stabilizes at a level incompatible with fracture resistance, or if cardiovascular adaptation leads to chronic dysfunction, no amount of time will convert that state into health. A mission tolerates decline. Survival requires stability. Closed life support system further expose the difference between missions and survivability. On temporary missions, small inefficiencies are manageable. Filters can be replaced. Components can be shipped from Earth. Nutrient imbalances can be corrected externally. Over decades, those inefficiencies compound. Trace losses of water, oxygen, and nutrients accumulate. Microbial ecosystems drift. Chemical byproducts build up. On Earth, ecosystems self-correct through vast, complex feedback loops. On Mars, every loop is artificial and limited. A mission only needs systems to function long enough. Survival requires that they function indefinitely without external correction. Food production highlights this constraint sharply. Temporary missions rely heavily on stored food and limited supplemental growth experiments. Survivability requires full nutritional independence. That means consistent production of calories, proteins, fats, vitamins and trace elements in correct ratios. It also means maintaining a stable human gut microbiome, which depends on dietary diversity and environmental exposure that Mars does not naturally provide. Short missions can ignore slow nutritional degradation. Over generations, even minor deficiencies alter development, immunity, and fertility. Time does not solve this, it amplifies it. Medical risk is also treated differently in missions than in survivability studies. Astronauts are screened extensively and represent a small, exceptionally healthy subset of the population. This selection bias hides environmental risk. Survivability requires supporting infants, children, pregnant individuals, and aging adults. Many conditions that are manageable or rare in a selected adult population become common and dangerous in a full demographic spectrum. Temporary missions do not test this. Survivability demands it. Infrastructure decay adds another layer. On a mission, wear and tear is acceptable as long as systems last through the planned timeline. For survivability, maintenance must be continuous and sustainable, using local resources. Mars offers limited raw materials, extreme temperature swings, pervasive dust, and radiation-driven material degradation. Over time, the maintenance burden increases, not decreases. A settlement that functions for 10 years may require exponentially more effort to function for 50. Missions never reach this phase. Survivability lives in it. Psychological and cognitive effects follow the same pattern. Short-term isolation and confinement are stressful but manageable. Long-term exposure to radiation and altered sleep cycles affects cognition, memory, and emotional regulation in ways that accumulate slowly. Temporary missions can end before these effects significantly impair function. Survivability cannot choose that cutoff. Cognitive decline over generations undermines education, problem-solving, and social stability, all of which are necessary to maintain complex systems in a hostile environment. The most important difference, however, lies in reproduction. Temporary missions avoid it entirely. Pregnancy, childbirth, and child development are excluded from mission design because the risks are unknown and potentially severe. Survivability cannot avoid them. It must face radiation exposure to developing embryos, altered gravity during organ formation, and limited medical intervention capacity. If reproduction cannot occur safely and repeatedly, survivability fails regardless of how successful missions appear. This is why scientists do not extrapolate from missions to permanence. The conditions that allow a mission to succeed are deliberately insulated from the full consequences of the environment. Survivability removes that insulation. It exposes every system, biological and mechanical, to continuous stress without a planned endpoint. Time is often presented as an ally, as if staying longer will somehow make Mars more hospitable. In reality, time is the stress multiplier. Every harmful factor on Mars acts continuously. Radiation accumulates, gravity effects compound, system inefficiencies grow, biological damage propagates across generations. Temporary missions work because they end. Survivability fails because it does not. The discovery: why scientists are now saying never. For decades, Mars was treated as a difficult destination, not an impossible one. The problems were framed as technical challenges waiting for better solutions. Rockets could be improved, habitats could be reinforced, life support systems could be refined. In that mindset, Mars was simply Earth with worse conditions, a hostile place that humans would eventually tame with enough ingenuity and persistence. That assumption shaped public messaging, funding priorities, and even how missions were designed. But that framing began to collapse when real data replaced theoretical optimism, and when multiple fields of science started reaching the same uncomfortable conclusion independently of one another. The shift did not come from one dramatic announcement or a single groundbreaking paper. It came slowly as evidence accumulated from Mars itself and from the human body under long-term space exposure. What changed was not technology, but understanding. Scientists began to realize that the core obstacles were not mechanical or logistical, but biological, and biology does not negotiate the way engineering does. Materials can be strengthened. Systems can be redesigned. The human body cannot be rewritten to function indefinitely in an environment it did not evolve for. One of the earliest cracks in the Mars optimism came from radiation measurements taken directly on the Martian surface. Before rovers like Curiosity, radiation exposure estimates were largely theoretical, built from orbital data and models of solar activity. Curiosity carried an instrument specifically designed to measure radiation levels during the journey to Mars and after landing. What it recorded was not just higher radiation than Earth, which was expected, but consistently high radiation with no meaningful periods of relief. Mars is exposed to galactic cosmic rays and solar energetic particles almost constantly because it lacks a global magnetic field and has only a thin atmosphere. Curiosity's data showed that this exposure is not an occasional hazard, but a permanent condition of the planet. When Perseverance arrived years later with more advanced instruments, scientists hoped for nuance or variability that might suggest safer regions or manageable cycles. Instead, the measurements confirmed the earlier findings. Radiation levels varied slightly with solar activity, but the baseline remained far above what human biology can tolerate over long periods. This was not radiation that could be avoided by scheduling missions carefully or waiting out storms. It was structural radiation, woven into the environment itself. Shielding could reduce exposure, but not eliminate it without creating secondary radiation effects that introduce their own biological risks. At the same time, a second stream of evidence was coming from much closer to home, aboard the International Space Station. The ISS was originally seen as a stepping stone toward Mars, a place to prove that humans could adapt to space over long durations. Early missions suggested that the human body could adjust to microgravity and elevated radiation if given enough time and countermeasures. But as missions extended from months to years, and as astronauts flew multiple long-duration missions across their careers, a different pattern emerged. Detailed medical monitoring revealed that bone density loss did not simply slow down or stop after an initial adjustment period. It continued. Muscle atrophy persisted despite rigorous exercise protocols. The cardiovascular system adapted in ways that reduced efficiency under normal gravity. Fluid shifts altered eye structure, leading to vision problems that sometimes failed to fully reverse after returning to Earth. More concerning was the evidence of cumulative damage effects that stacked rather than reset, indicating that the human body was not finding a stable equilibrium in space, but slowly degrading under continuous stress. Mars would not provide relief from these stresses. Unlike the ISS, there is no rapid return to Earth, no medical evacuation, no opportunity for long-term recovery in full gravity. Mars' gravity is lower than Earth's, but higher than microgravity, a condition once hoped to be a compromise that might preserve human health. However, emerging data suggested that partial gravity does not necessarily trigger normal biological maintenance processes. Bone remodeling, muscle retention, and cardiovascular regulation appear to depend on specific gravitational thresholds. Below those thresholds, degradation continues, just more slowly. Over decades, slow damage is still damage. Another critical shift came from improved models of Mars' atmosphere and its ongoing loss. For years, the thin Martian atmosphere was treated as a static limitation that could be engineered around. Pressurized habitats and sealed environments were assumed to be sufficient. But missions like MOVEN revealed that Mars is still actively losing its atmosphere to space due to constant interaction with the solar wind. Without a magnetic field to deflect charged particles, the planet's upper atmosphere is gradually stripped away. This ongoing loss matters because it reinforces radiation exposure and limits any long-term atmospheric recovery. Mars is not just thin, it is unprotected and deteriorating. Updated atmospheric models showed that restoring a dense, Earth-like atmosphere would require energy and material far beyond what Mars can realistically provide. The planet lacks the internal heat and magnetic dynamo that protect Earth. This is not a temporary setback or a technological gap. It is a fundamental planetary difference. Any human habitat on Mars would exist as a sealed bubble under constant external assault, with no planetary systems acting as a backup. On Earth, small failures are often absorbed by the environment. On Mars, failure is immediate and unforgiving. The most decisive evidence, however, came from long-term studies of bone density, organ function, and systemic health under reduced gravity and elevated radiation. Bone loss rates observed in astronauts were not just concerning for adults, but alarming when projected across a full lifespan, especially starting from childhood. Bones weakened beyond safe thresholds. Fracture risk increased. Recovery slowed. When researchers modelled these effects over multiple decades, the outcome was clear. The skeletal system does not maintain structural integrity under sustained reduced gravity. Organ systems showed similar trends. The kidneys struggled with altered fluid dynamics. The immune system showed signs of suppression and chronic inflammation. Hormonal regulation drifted. Neural tissue, particularly in the brain, showed vulnerability to radiation-induced damage that accumulates over time. These are not problems that wait for a breakthrough material or a smarter machine. They are direct consequences of placing human biology in an environment it was never meant to endure indefinitely. What changed the scientific conversation was not any single data point, but the way these findings aligned. Radiation, gravity, atmospheric exposure, and physiological degradation were all reinforcing one another. Solutions proposed for one problem often worsened another. More shielding increased mass and secondary radiation. Artificial gravity concepts remained unproven at scale. Closed habitats increased dependence on perfect system performance. Every fix introduced new risks, and every risk compounded over time. This is when the language began to change behind the scenes. Mars stopped being described as merely challenging and started being treated as biologically incompatible. Not because humans could not visit, but because the human body does not reach a stable state there. There is no plateau where damage stops accumulating, no balance point where systems adapt and hold. Mars pushes continuously, and biology gives way slowly, predictably, and permanently. This realization did not kill Mars exploration, but it reframed it completely. Mars could still be studied, explored, visited. But the idea of humans surviving there as a self-sustaining population began to collapse under the weight of the evidence. Why optimism collapsed. For a long time, belief in human survival on Mars was carried by a familiar idea that every serious obstacle is at its core an engineering problem. If radiation is dangerous, build thicker shielding. If gravity is too weak, invent countermeasures. If the environment is hostile, isolate humans from it. This way of thinking had worked before. Humans had crossed oceans, flown through the atmosphere, and walked on the moon by turning natural barriers into technical challenges. Mars was placed in the same category. Difficult, yes, but ultimately solvable with enough innovation and time. What collapsed that optimism was the realization that Mars does not fail at a single point that can be reinforced or redesigned. It fails at the level of biology itself. Engineering can protect machines from Mars. It cannot rewrite how human cells respond to radiation, how bones respond to gravity, or how organs respond to decades of altered physical conditions. Once scientists separated what technology can fix from what biology cannot tolerate, the problem changed shape entirely. Engineering problems behave in predictable ways. They improve with better materials, better models, and better testing. Biological problems do not. The human body is not modular. You cannot strengthen one system without affecting others. On Mars, every proposed technical solution began colliding with biological consequences that could not be engineered away. Radiation shielding is a clear example. Thick walls, underground habitats, and heavy materials can reduce exposure, but they introduce mass penalties that limit construction, increase launch requirements, and create secondary radiation effects when high-energy particles interact with dense shielding. Even when exposure is reduced, it is never eliminated, and biology responds to cumulative damage, not averages. The same pattern appeared with gravity. Engineers proposed exercise regimes, mechanical loading devices, and even rotating habitats to simulate gravity. But these solutions only address part of the problem and only partially. Human skeletal and cardiovascular systems evolved under continuous, full gravity, not intermittent or simulated loads. Bone density loss observed in spaceflight does not halt at a safe level. It continues as long as the gravitational signal remains below the threshold the body requires. Engineering can slow the damage, but slowing damage is not the same as preventing it, and survivability depends on prevention, not delay. Closed habitats were another pillar of optimism. The idea was simple. If Mars itself is hostile, seal humans off from it completely. Create controlled environments where temperature, pressure, and air composition are carefully maintained. This works for missions. It fails over long timescales. Closed systems are never perfectly closed. Materials degrade, microbes evolve, trace chemical imbalances accumulate. On Earth, massive natural systems absorb and correct these errors. On Mars, every correction must be deliberate, energy-intensive, and flawless. Biology does not forgive small, repeated stresses. Over years and decades, minor failures compound into systemic breakdowns. Food production revealed the same hard limits. Engineers focused on calories and yield, but human nutrition is not just energy intake. It involves complex interactions between diet, gut microbiota, immune function, and development. Mars offers no natural soil ecosystem to support this complexity. Hydroponic systems can grow plants, but they do not recreate the biological diversity that human bodies evolved alongside. Over time, reduced dietary complexity alters gut microbiomes, which in turn affect nutrient absorption, immunity, and even neurological health. These effects are subtle at first and devastating over generations. No amount of mechanical efficiency fixes missing biology. Medical care exposed another false assumption. Optimism often relied on the idea that advanced medicine would compensate for environmental harm. But medicine treats symptoms. It does not eliminate causes. Radiation-induced DNA damage, for example, can be monitored, but it cannot be reversed. Degeneration caused by reduced gravity can be managed, but not fully corrected without restoring the missing physical conditions. Mars medicine would face the same constraints as Earth medicine, with fewer resources and greater exposure. Engineering can deliver equipment. It cannot change the fact that some injuries accumulate faster than they can be repaired. As these realities became clearer, scientists began to stop asking how to make Mars survivable and started asking a more uncomfortable question. Does the human body have a stable operating state on Mars at all? Stability is the key concept. On Earth, despite stress, the body tends to return to equilibrium. Systems are stressed and then recover. On Mars, data suggested that systems drift continuously away from healthy baselines. Bone density declines, muscle mass decreases, immune function weakens, neurological risk increases. There is no point where the decline naturally stops. This is the definition of a biological hard limit. It is not a wall you crash into immediately. It is a slope you cannot climb back up. You can slow your descent. You can make it gentler. But you cannot stop it without changing the environment in ways that Mars does not allow. This is why optimism did not fade gradually. It collapsed once this pattern became clear. Engineers realized that their solutions were buying time, not creating sustainability. Biologists recognized that time was the enemy. Every year on Mars would add damage that no system could fully undo. Every generation would inherit a slightly worse starting point than the last. At that moment, the framing changed. Mars was no longer compared to hostile places on Earth that humans eventually mastered. It was compared to environments that fundamentally reject human biology, places where survival is temporary by definition, not because of danger, but because of incompatibility. Mars does not support a stable human biological state. Engineering can build shelters. It can extend missions. It can protect individuals for a time. What it cannot do is turn an environment that continuously damages the human body into one where a human population can persist indefinitely. Mars has no magnetosphere, and that breaks everything. To understand why Mars is fundamentally hostile to human survival, you have to start with something invisible, something most people never think about, something so constant on Earth that we barely notice it exists: the planetary magnetic field. Without it, nothing else about survival on Mars even makes sense to discuss, because the magnetosphere is not just a feature of Earth. It is the reason Earth remains a living world at all. Earth's magnetosphere is generated deep inside the planet by the motion of molten iron in its core. This movement creates a vast magnetic bubble that extends tens of thousands of kilometers into space. It is not static. It flexes and shifts as the sun releases energy toward us, but its role is constant. It deflects high-energy charged particles from the sun and from deep space, redirecting them around the planet instead of allowing them to slam directly into the atmosphere and the surface. Without this shield, Earth would be exposed to a continuous storm of radiation, powerful enough to strip away air, disrupt chemistry, and damage living tissue at the molecular level. This magnetic field works hand in hand with Earth's thick atmosphere. When high-energy particles do get through, the atmosphere absorbs much of their energy before they ever reach the ground. Together, these two systems form a layered defense. The magnetosphere keeps most radiation away. The atmosphere handles what remains. This combination protects surface life, preserves the atmosphere itself, and stabilizes the chemical environment that biology depends on. It also shields DNA from constant bombardment by ionizing radiation, which breaks molecular bonds, causes mutations and triggers cancer. Mars has none of this protection. Early in its history, Mars did have a magnetic field. Geological evidence shows that roughly 4 billion years ago, Mars possessed a molten core capable of generating a global magnetosphere similar in function, though weaker than Earth's. Then something changed. The planet cooled faster than Earth because it is smaller and lost internal heat more quickly. As the core cooled and solidified, the dynamo shut down, the magnetic field collapsed, and once it was gone, Mars became exposed. Without a magnetosphere, the solar wind began interacting directly with the Martian atmosphere. Charged particles from the Sun slammed into the upper layers of gas, knocking atoms and molecules into space. Over millions of years, this process stripped Mars of most of its atmosphere. What remains today is thin, patchy, and unable to provide meaningful protection. This loss was not a one-time event. It is ongoing. Mars is still bleeding atmosphere into space, particle by particle, because nothing stands between it and the Sun. This matters because atmosphere is not just air. It is pressure, it is insulation, it is radiation shielding. On Earth, our atmosphere is thick enough that it absorbs and scatters incoming radiation. On Mars, the atmosphere is so thin that it provides almost no defense. Radiation that would be stopped high above Earth's surface reaches the ground on Mars with much of its energy intact. NASA's rovers were sent to quantify this risk, not speculate about it. Curiosity carried the Radiation Assessment Detector, an instrument designed to measure exactly how much radiation reaches the Martian surface. During its cruise to Mars, it recorded exposure levels in deep space. After landing, it continued collecting data day after day. The results were sobering. The average radiation dose on the Martian surface was measured at roughly 40 to 50 times higher than what humans experience on Earth's surface. And this was not during extreme solar events. This was the background environment, the normal state of the planet. Perseverance later confirmed these findings with newer instruments and longer observation periods. Different locations showed similar results. There were fluctuations, but no safe zones, no natural shelters, no meaningful seasonal relief. Mars is bathed in radiation constantly, from all directions, because there is nothing to deflect it and very little to absorb it. This radiation is not like the low-level background radiation people encounter on Earth. It includes high-energy galactic cosmic rays, particles accelerated to near light speed by distant supernovae, as well as solar energetic particles released during solar storms. These particles penetrate deep into materials. They pass through skin, through muscle, through bone. They interact with atoms inside cells, shattering molecular bonds and creating cascades of secondary particles that cause additional damage as they pass through tissue. On Earth, most of these particles never reach the surface. They are deflected by the magnetosphere or absorbed by the atmosphere. On Mars, they reach the ground almost unimpeded. This is not an abstract danger. It is a measured, continuous exposure that affects every cell in the body simultaneously. The absence of a magnetosphere also explains why Mars cannot hold onto water in liquid form on its surface today. Without atmospheric pressure and protection, water either freezes or sublimates directly into vapor and is carried away by the solar wind. This reinforces the feedback loop. Less atmosphere means more radiation. More radiation means more atmospheric loss. The planet spiraled into its current state long before humans ever looked up at it, and there is no natural mechanism left to reverse that process. When scientists realized the full implications of Mars lacking a magnetosphere, it reframed every other discussion. Radiation was no longer just a hazard to be managed. It was a permanent environmental condition. Atmospheric loss was no longer a past event. It was an ongoing process. and biological exposure was no longer occasional. It was constant from birth to death. This is why the magnetosphere is considered the first and most critical failure point for human survival on Mars. Without it, the planet is fundamentally unshielded. Every human habitat would exist inside an artificial bubble, surrounded by an environment that actively damages biological tissue at the molecular level. There is no natural backup system, no planetary scale protection, no margin for error. Earth works because it is a layered system. If one defense weakens, another compensates. Mars has no such redundancy. Once the magnetosphere disappeared, everything else followed. The atmosphere thinned, radiation increased, surface conditions deteriorated, biology lost its shield. This is not a challenge humans face anywhere else in the solar system in quite the same way. Even the Moon, while lacking a magnetosphere, is not proposed as a permanent, self-sustaining human world for exactly this reason. Mars, despite its size and distance, is closer to deep space than it is to Earth in terms of protection. Understanding this changes how Mars must be viewed. It is not a rough version of Earth waiting to be fixed. It is a planet that lost the very system that makes surface life viable. And once that system is gone, no amount of surface construction or local engineering can replace it on a planetary scale. This is where the real problem begins, because the absence of a magnetosphere is not something you can build around easily. It is something you must fight constantly at every level, for every moment humans remain there. And that fight never ends. Why shielding doesn't solve it. If the planet itself could not protect humans, then perhaps technology could. Thicker walls, buried habitats, layers of regolith, advanced materials. The logic seems straightforward. Radiation is energy. Energy can be blocked. Build enough protection and the problem goes away. This idea dominated Mars planning for decades, and on the surface, it sounds reasonable. But as radiation science matured and long-duration exposure data accumulated, researchers realized that this assumption was dangerously incomplete. Radiation does not behave like rain. You cannot simply stand under a roof and stay dry. When high-energy particles collide with shielding material, they do not stop politely at the surface. They interact with atoms inside the shielding itself, shattering nuclei and releasing new particles in the process. These secondary particles can be just as dangerous as the original radiation, and in some cases, more damaging to human tissue. This is where the concept of secondary particle cascades becomes central to the Mars problem. When galactic cosmic rays strike dense materials like metal or concrete, they produce showers of secondary radiation, including neutrons, gamma rays, and fragmented atomic nuclei. Neutrons are particularly problematic because they carry no electric charge. This means they are not easily deflected and can pass deeply into living tissue before interacting. Once they do, they cause widespread molecular disruption, especially in water-rich environments like the human body. This turns shielding from a simple barrier into a radiation amplifier under certain conditions. Experiments conducted using particle accelerators on Earth allowed scientists to simulate cosmic radiation interacting with different materials. The results were consistent and deeply concerning. Increasing shielding thickness did reduce some forms of radiation, but it also increased neutron production. In some configurations, astronauts inside heavily shielded environments experience radiation doses similar to or even higher than those behind thinner barriers. The radiation profile changed, but the biological damage did not disappear. This forced a shift in how scientists evaluated risk. It was no longer enough to measure how much radiation reached the habitat interior. Researchers had to measure what kind of radiation reached human tissue and how it interacted at the cellular and genetic level. This is where biology overtook engineering. Ionizing radiation damages DNA in several ways. It breaks single strands, it breaks double strands, it alters chemical bases. Cells can repair some of this damage, but repair mechanisms are not perfect. Errors accumulate, mutations persist. Over time, the genome becomes unstable. On Earth, these processes happen slowly, and the body's repair systems keep up most of the time. On Mars, the rate of damage is dramatically higher, and it never stops. Long-duration data from astronauts aboard the International Space Station revealed that even in low Earth orbit, where Earth's magnetosphere still provides partial protection, radiation exposure caused measurable genetic changes. Astronauts showed increased chromosomal aberrations, persistent DNA damage markers, and altered gene expression long after returning to Earth. These effects were observed after missions lasting months. Mars missions would involve years of exposure in an environment with far less protection. Bone marrow is especially vulnerable to radiation. It is where blood cells are produced, and damage there affects the entire immune system. Studies showed reduced white blood cell production and altered immune responses in astronauts after extended missions. This leads to increased infection risk, slower wound healing, and impaired cancer surveillance. On Mars, where exposure would be higher and continuous, this degradation would not stabilize. It would progress. Neural tissue is also affected. Radiation does not just cause cancer, it alters brain structure and function. Animal studies exposed to simulated cosmic radiation showed inflammation in brain tissue, reduced neurogenesis, and cognitive decline. Memory, attention, and decision-making were all impacted. These are not abstract concerns. They affect the ability to work, adapt, and function in complex environments. Over years, these changes accumulate and become permanent. The most critical insight came when scientists began modelling multi-generational exposure. Radiation damage does not reset between generations. Mutations in reproductive cells can be passed on. This means children conceived on Mars would not start with clean genetic material. They would inherit a genome already stressed by radiation. Studies in radiation biology show that even small increases in mutation rates can lead to developmental abnormalities, reduced fertility, and increased disease prevalence over generations. Shielding does nothing to solve this at a biological level. Even if habitats reduce exposure somewhat, they cannot eliminate it. People still need to move, they still need to work, they still need to maintain systems. Every exposure adds damage. Over years, that damage compounds. Over decades, it reshapes the population's health profile. This is not survivability. It is slow biological erosion. Another problem is duration. Engineering solutions are evaluated over years. Biology operates over lifetimes. A habitat wall that performs adequately for 10 years does not solve what happens over 50, or in 100, or 3 generations. Materials degrade, gaps form. Maintenance becomes harder. Every repair requires exposure. Every failure increases risk. The longer the timeline, the more biology loses the race. Radiation shielding also competes with other constraints: mass limits, structural integrity, thermal control, life support integration. You cannot build arbitrarily thick walls without consequences. Every added layer increases launch cost, construction complexity, and mechanical stress. Underground habitats reduce exposure but introduce other problems, including isolation, limited mobility, and psychological strain, which in turn affect immune and neurological health. These systems are interconnected, and shielding cannot be optimized in isolation. As these findings accumulated, optimism began to collapse, not because engineers failed, but because biology set boundaries that engineering could not cross. You can build better machines. You cannot redesign human DNA to tolerate constant high-energy radiation without fundamentally changing what humans are. The problem was no longer how to survive Mars. It was whether humans, as biological organisms, are compatible with Mars at all. The planet does not merely lack comfort, it lacks the conditions required to preserve genetic integrity over time. Shielding can delay damage, it cannot prevent it. And delayed damage still accumulates into failure when the timeline extends beyond a single mission. Radiation versus the human body. What the data actually shows. When scientists talk about radiation on Mars, they are not talking about a vague danger or a distant risk that might show up decades later if you're unlucky. They are talking about a constant, measurable, biological assault that begins the moment a human leaves Earth's magnetic shield and does not stop for the rest of that person's life. This is not science fiction. This is not worst-case speculation. This is direct data collected from astronauts, radiation detectors, medical imaging, post-flight neurological testing, and long-term epidemiological models built from real human tissue damage. On Earth, radiation exposure is something the human body evolved alongside. We receive small doses from cosmic rays, radioactive elements in the ground, medical imaging, and even the food we eat. The key word is small. Earth's atmosphere and magnetosphere reduce incoming high-energy radiation by orders of magnitude before it ever reaches human DNA. Mars does not do that. Mars exposes the human body to radiation types and intensities that terrestrial biology has never had to survive under continuously. And the difference is not linear, it is exponential. Radiation on Mars comes in several forms, but the most biologically destructive are galactic cosmic rays and solar energetic particles. Galactic cosmic rays are high-energy particles accelerated by supernovae and other extreme astrophysical events, moving close to the speed of light. These particles do not behave like the radiation we are familiar with in hospitals or nuclear plants. When they strike human tissue, they do not gently pass through. They slam into atoms inside cells, shatter molecular bonds, and trigger cascades of secondary particles that spread damage far beyond the original impact point. This matters because biological damage is not just about how much radiation you receive, but how that radiation deposits energy at the microscopic level inside cells, DNA strands, and neural tissue. NASA's own measurements taken by the Curiosity rover's radiation assessment detector and confirmed by Perseverance show that radiation levels on the Martian surface average roughly 0.67 millisieverts per day. That number sounds abstract until it's put into context. On Earth, the average person receives about 2.4 millisieverts per year from all natural sources combined. On Mars, astronauts would receive that amount roughly every 4 days. Over the course of a year, a human on Mars would absorb around 240 millisieverts, not counting solar storm spikes. That level of exposure is not survivable in a long-term biological sense, and the reason becomes clear when you look at what radiation actually does inside the body. The most immediate concern scientists evaluate is cancer risk, because cancer is relatively easy to model statistically. NASA uses probabilistic risk assessment models that estimate the likelihood of radiation-induced fatal cancer over a lifetime. These models are based on data from atomic bomb survivors, medical radiation exposure, and astronaut flight histories. For low Earth orbit missions, these models already push the upper limits of what NASA considers acceptable risk. For Mars missions, the numbers break the framework entirely. A single round-trip Mars mission, including transit and surface stay, is estimated to expose astronauts to between 600 and 1,000 millisieverts, depending on solar activity and mission duration. NASA's career radiation exposure limit for astronauts is designed to keep the added lifetime cancer risk below roughly 3%. a Mars mission alone would likely exceed that limit before the crew even returns to Earth. For someone attempting to live on Mars permanently or to reproduce there, cancer risk becomes almost beside the point, because cancer is only one of several irreversible biological failures triggered by chronic high-energy radiation. The central nervous system is where the problem becomes far more severe and far less solvable. Unlike skin or blood cells, neurons do not regenerate in large numbers. Damage to neural tissue accumulates, and radiation damage to the brain is not uniform or predictable in the way cancer risk is. Studies using animal models exposed to Mars-like radiation have shown structural changes in the hippocampus and prefrontal cortex, regions responsible for memory, decision-making, emotional regulation, and spatial navigation. These are not subtle effects. Researchers have observed reduced synaptic density, altered neurotransmitter signaling, chronic neuroinflammation, and impaired neurogenesis. When similar studies were extended to astronauts aboard the International Space Station, who experience elevated but still relatively low radiation compared to Mars, measurable cognitive effects began to appear. Post-flight testing has documented declines in attention, processing speed, and executive function in some astronauts, along with changes in brain structure detected through MRI scans. These changes occurred after missions lasting only 6 to 12 months, under radiation levels far below those expected on Mars. The implication is not that astronauts become incapacitated immediately, but that the human brain is measurably altered by sustained exposure to space radiation in ways that do not fully reverse after returning to Earth. On Mars, this becomes a permanent condition. The brain would be subjected to continuous bombardment without periods of recovery. Over time, radiation damages not only neurons, but also the supporting glial cells that maintain neural networks, regulate inflammation, and protect against oxidative stress. This leads to chronic neuroinflammation, which is a known driver of neurodegenerative diseases. In animal studies, Mars-relevant radiation exposure has produced pathological markers associated with Alzheimer's disease, including increased beta-amyloid accumulation and tau protein abnormalities. These are not symbolic similarities. They are the same molecular processes that drive dementia on Earth. Cognitive decline under these conditions is not hypothetical. It is a direct consequence of how radiation interacts with brain tissue. Tasks requiring sustained attention, long-term planning, and complex problem-solving degrade first. Emotional regulation follows, increasing anxiety, depression, and impulsivity. For a Mars settlement, this is catastrophic because survival in a hostile environment depends on flawless decision-making, social cohesion, and rapid response to emergencies. A population experiencing gradual, unavoidable cognitive degradation cannot maintain a functioning society, regardless of how advanced its engineering systems are. Beyond the brain, radiation affects the cardiovascular system in ways that further undermine long-term survival. High-energy radiation damages endothelial cells lining blood vessels, accelerating atherosclerosis and increasing the risk of heart attacks and strokes. Studies of cancer patients who received radiation therapy show elevated cardiovascular disease decades later, even when exposure was localized. On Mars, radiation exposure would be systemic and continuous, affecting every vessel in the body. This is not an aging problem. It is a cumulative injury problem where biological repair mechanisms cannot keep pace with ongoing damage. The immune system is also compromised. Radiation suppresses bone marrow function, reducing the production of white blood cells and weakening immune response. Astronauts already experience immune dysregulation during spaceflight, including reactivation of latent viruses such as Epstein-Barr and varicella zoster. On Mars, this immune suppression would be chronic. increasing susceptibility to infections and reducing the body's ability to repair damaged tissue. In a closed environment with limited medical resources, even minor infections could become life-threatening. Perhaps the most overlooked consequence of radiation exposure is its effect on reproductive health and genetic integrity. Radiation damages germ cells, increasing mutation rates in sperm and eggs. This is not just a fertility issue, it is a generational issue. Elevated mutation rates increase the likelihood of birth defects, developmental disorders, and inherited diseases. On Earth, radiation workers are subject to strict exposure limits precisely to protect reproductive health. On Mars, those limits would be exceeded continuously, making multi-generational human survival biologically unstable. What makes radiation uniquely devastating is that it does not produce a single failure point. It degrades multiple systems at once, slowly, invisibly, and irreversibly. Cancer may appear years later, but cognitive decline, immune dysfunction, cardiovascular damage, and genetic instability begin much earlier. These effects interact, compounding one another in ways that no current medical intervention can fully prevent or reverse. This is why radiation is not just another hazard to be engineered around. It is a fundamental environmental incompatibility between Mars and the human organism. The data does not suggest that humans might struggle on Mars. It shows that the human body at a cellular and molecular level is not designed to operate under constant high-energy radiation exposure without Earth's protective systems. The longer the exposure lasts, the more certain the damage becomes, and the less meaningful survival becomes as a scientific term. And this leads directly to the next question scientists were forced to confront. At what point does the concept of acceptable risk collapse entirely? Not because humans are unwilling to take danger, but because the biology itself stops cooperating? When acceptable risk stops meaning anything. For decades, space agencies have relied on a concept called acceptable risk to justify sending humans into dangerous environments. Every astronaut knows the risks. Every mission accepts that spaceflight is not safe in the everyday sense. But what most people don't realize is that acceptable risk has a very specific scientific meaning, and that meaning completely collapses once mission duration crosses a certain biological threshold. Mars crosses that threshold long before any permanent human presence could stabilize. NASA does not treat radiation risk casually. It is one of the most tightly regulated aspects of human spaceflight. Every astronaut has a lifetime radiation exposure limit based on age and sex, calculated to keep the probability of radiation-induced fatal cancer below approximately 3% above baseline. This is not a moral guideline. It is a mathematical one, derived from decades of epidemiological data and refined continuously as new biological evidence becomes available. These limits already assume that astronauts are among the healthiest humans alive, selected for exceptional physical and genetic resilience. In low Earth orbit aboard the International Space Station, astronauts accumulate radiation exposure at a rate of roughly 80 to 160 millisieverts per 6-month mission. Even at those levels, NASA carefully tracks cumulative dose, limits mission frequency, and may ground astronauts permanently once their career exposure approaches the cap. This is happening now, in an environment still partially protected by Earth's magnetosphere. A Mars mission does not gently exceed these limits, it annihilates them. The transit to Mars alone exposes astronauts to deep space radiation levels far higher than anything experienced in Earth orbit. Estimates vary, but a typical 6 to 9 month journey each way adds roughly 300 to 400 millisieverts per leg. That means that before an astronaut even sets foot on Mars, they may already be near or beyond their lifetime career radiation allowance. Then comes surface exposure, which continues relentlessly, day after day. with no geomagnetic protection and only minimal atmospheric shielding. At that point, the language of acceptable risk becomes meaningless because the exposure is no longer bounded. Acceptable risk only works when exposure is finite and controlled. Mars exposure is neither. It does not taper off, it does not stabilize, it accumulates until biology fails. This is where the difference between missions and settlement becomes unavoidable. A mission assumes that damage occurs but stops at some point, allowing the body a chance to recover or at least plateau. A settlement assumes continuous exposure for years, decades, and eventually generations. There is no version of NASA's radiation framework that supports that scenario, because it violates the foundational assumption that risk can be capped. Some argue that acceptable risk is a policy choice, not a physical law, and that future explorers may simply accept higher danger. That argument collapses when you look at how radiation damage actually unfolds over time. Radiation does not produce a single dramatic event that someone can bravely endure. It produces gradual systemic degradation that erodes function long before death occurs. A person does not suddenly die from radiation exposure on Mars. They become less capable of surviving there. Cancer models illustrate this clearly. As cumulative dose increases, the probability of developing multiple cancers rises non-linearly. It is not just a higher chance of one cancer, it is a higher chance of overlapping malignancies affecting different organs at different times. Treatment on Mars would be limited, and immune suppression caused by radiation would reduce the body's ability to respond even to early-stage disease. The longer exposure continues, the less meaningful early detection becomes. But cancer is still not the primary reason acceptable risk collapses. The primary reason is neurological decline. Unlike cancer probability, cognitive degradation does not operate on a binary alive or dead scale. It reduces judgment, memory, emotional control, and problem-solving ability gradually. A person may still be alive, still walking, still breathing, while being increasingly incapable of maintaining life support systems, responding to emergencies, or participating in a functioning community. NASA has no acceptable risk model for permanent cognitive erosion because it has never needed one. Astronauts are expected to perform at peak cognitive capacity throughout their missions. Even small declines are treated seriously. On Mars, declines would not be small, and they would not stop. The idea of accepting that level of impairment is not bravery, it is operational failure. Radiation exposure also interacts with other spaceflight stresses in ways that compound risk beyond any single model. Microgravity weakens bones and muscles. Radiation impairs bone marrow and vascular health. Isolation and confinement strain mental health. Radiation increases neuroinflammation and disrupts neurotransmitter balance. Each of these factors is manageable on its own, within limits. Together, over years, they push the human organism outside the envelope it evolved to function within. This is why optimism around Mars survivability collapsed so sharply among scientists who work directly with human health data. The problem was never that Mars is hard. The problem is that Mars violates too many biological constraints at once, for too long, without relief. Engineering solutions can mitigate discrete hazards. They cannot rewrite how DNA repairs itself, how neurons regenerate, or how cumulative damage reshapes physiology. Radiation shielding is often proposed as the fix, but acceptable risk models already account for shielding, and even optimistic projections fail to bring exposure anywhere near safe, long-term levels. Thick shielding introduces mass penalties that make launch impractical. Buried habitats reduce radiation but do not eliminate it, and they introduce psychological and logistical challenges that further strain human health. Even under ideal shielding scenarios, secondary particle radiation still penetrates, continuing to damage tissue at levels far above Earth norms. The deeper issue is that acceptable risk assumes a temporary sacrifice for a lasting gain. Mars requires permanent sacrifice with no biological stabilization point. Every year lived there worsens health outcomes. Every child conceived there inherits elevated genetic risk. Every generation compounds the damage. At that point, the question is no longer whether humans can survive Mars. It is whether the definition of survival still applies when health inevitably and irreversibly declines. Acceptable risk requires a boundary. Mars does not provide one. By the time a Mars colony could theoretically become self-sustaining, the cumulative radiation exposure of its inhabitants would already exceed every known threshold for long-term human health, cognition, and reproduction. Not because the mission failed, but because the environment never stopped doing damage. How long can human biology function before survival becomes an illusion created by short-term endurance rather than long-term viability? That question does not have a hopeful answer, and the data does not leave room for a different one. Mars gravity is slowly lethal. When people think about living on Mars, they often picture spacesuits, red dust, and dramatic storms. What they almost never picture is the slow, invisible erosion of the human body under a gravity that is far weaker than what it evolved to rely on. Mars's gravity is only about 38% of Earth's. That means if you weigh 100 kilograms on Earth, you would weigh 38 on Mars. That sounds like a relief at first. It sounds fun. Astronauts would jump higher, lift heavier things with less effort, and experience something almost like freedom. But biology does not see it that way. Evolution built the human body to function in full Earth gravity, with every bone, muscle, organ, and circulatory system calibrated to that force. Remove most of it, and the body begins to unlearn how to exist. What we know about gravity's role in human physiology comes from decades of microgravity studies aboard the International Space Station and earlier space flights. These studies show that bone density begins to decline immediately once gravity is reduced, often at rates of 1 to 2% per month. Over 6 months, astronauts can lose 10% of critical bone mass, particularly in the spine, hips, and legs. This is not cosmetic, it is structural. Bones weaken until they can fracture under stresses that were once trivial, like bending over or lifting a light object. On Mars, gravity is not zero like in orbit, but it is not enough to fully stop these losses. Every step, every movement is slightly underloading the skeleton. Over years, this becomes a slow erosion that adds up, leaving the body fragile in ways that cannot be corrected by diet, exercise, or medicine alone. Muscles suffer in the same way. On Earth, every muscle works against gravity constantly, even when doing nothing consciously. In microgravity, this constant stimulus disappears, and muscle fibers atrophy. Astronauts can lose 20 to 30% of muscle mass after extended stays in orbit. While exercise mitigates some of this loss, it cannot fully reproduce the natural resistance provided by gravity. Mars's partial gravity is stronger than zero, yes, but it is far weaker than the baseline humans evolved with. Muscle atrophy would slow compared to orbit, but it would not stop. The legs, back, and postural muscles, the ones humans use to stand, walk, and support organs, would slowly weaken, leaving every inhabitant walking in a progressively deteriorating body. The cardiovascular system is equally vulnerable. The human heart and circulatory system evolved to pump blood vertically against a consistent gravitational pull. In microgravity, the heart shrinks, blood vessels lose elasticity, and fluid redistributes toward the head, causing vision and neurological issues. On Mars, gravity is partially restored, but not enough to fully stimulate the cardiovascular system in the way Earth does. Studies suggest that long-term exposure to 38% gravity could lead to persistent heart shrinkage, weakened vascular tone, and inefficient blood flow. Every organ in the body depends on adequate perfusion. Compromised circulation leads to fatigue, organ stress, and higher susceptibility to stroke or organ failure under even minor medical stress. The damage is subtle at first, almost invisible, but relentless, accumulating over months and years until the body's baseline capacity itself is degraded. Mars gravity is often underestimated because it is not immediately lethal. People can walk, lift, and move. They can live for months without dramatic crises. But the threat is cumulative, slow, and unavoidable. Unlike radiation, which can be blocked or mitigated, partial gravity cannot be engineered away. It is not a problem that can be solved with better spacesuits, exercise machines, or habitat design. It is a constant environmental stress built into the very structure of the planet. Every second spent walking, standing, or sitting in that reduced gravity gradually changes the skeleton, muscles, and circulatory system in ways that may eventually be irreversible. Long-term studies also show that even when astronauts return to Earth after months in microgravity, some changes never fully reverse. Bone density recovers only partially, muscle strength takes years to return, and cardiovascular adaptations leave lasting consequences. On Mars, these adaptations would never fully reset because the body would never return to Earth normal gravity. Over generations, the damage would compound. Humans are not biologically designed to adapt to partial gravity over multiple lifespans. That is why scientists now describe Mars gravity not just as a challenge, but as a fundamentally slow, lethal force acting on human biology. Why partial gravity doesn't fix it, the reproduction problem. Even if humans somehow survive the slow, unrelenting toll of Mars's gravity on bones, muscles, and the cardiovascular system, there is a problem far more fundamental: reproduction. Gravity is not just a force acting on standing humans. It is a shaping force for development itself. Every cell in a fetus, every organ forming in the womb, every blood vessel threading its way through tissues is calibrated to Earth gravity. Reduce that force to 38%, and we enter an environment no human has ever evolved to navigate during development. The implications are profound, immediate, and entirely untested. We know very little about fetal development in partial gravity, and what we do know comes from studies in microgravity. Animal studies in orbit have shown that microgravity alone can disrupt cell orientation, organ placement, and skeletal formation. Hearts may loop incorrectly, spines may fail to align, blood vessels may not connect efficiently. Even small deviations during early organogenesis, tiny structural differences that would be invisible at birth, can cause long-term functional deficits that manifest as circulatory failure, reduced organ capacity, or sudden organ collapse later in life. On Mars, gravity is not zero, but it is still far below Earth normal. There is no evidence that 38% gravity is sufficient for proper organ development. Every step of reproduction becomes a gamble. Every pregnancy carries unknown, likely severe, risks. The circulatory system is one of the first and most serious failures predicted in partial gravity reproduction. Human circulation relies on hydrostatic pressure gradients created by Earth gravity. In utero, blood flows from mother to fetus through a combination of maternal pumping, placental exchange, and fetal heart pressure. On Mars, these gradients are reduced. Studies suggest that reduced hydrostatic pressure could lead to hypoperfusion in critical fetal organs, including the brain and heart. The result may be developmental abnormalities, hypoxia, or even fetal death. There is no biological workaround for this. Unlike bones or muscles, which can at least partially adapt over time, Fetal development cannot be paused, retrained, or artificially loaded to Earth-normal conditions without technology that does not yet exist. Gravity also shapes structural orientation of internal organs. On Earth, the liver, stomach, kidneys, and intestines all form in precise spatial relationships, guided partly by gravitational cues during development. Disrupt those cues, and organs can rotate, compress, or fail to connect properly with major vessels. Animal experiments in microgravity have documented altered organ positioning in small mammals, with measurable functional consequences. For humans, this means even a successful live birth on Mars could result in systemic organ failures that do not appear immediately, but compromise long-term survival. Beyond organ placement, reproduction also faces hormonal and cellular challenges. Reduced gravity affects endocrine regulation in adults, which in turn regulates fertility, gamete quality, and pregnancy maintenance. Female reproductive cycles are disrupted under microgravity, and sperm quality degrades in male organisms after space exposure. Mars's gravity is stronger than zero, but there is no known threshold at which human reproductive systems operate normally. We do not have data to suggest that 38% gravity is sufficient to sustain gamete viability, maintain healthy hormone cycles, or support multiple pregnancies across generations. Every attempt at reproduction would be a step into biological uncertainty. This leads to an inescapable conclusion. Partial gravity does not solve the generational problem. Even if first-generation colonists survive, the next generation cannot be guaranteed. Mars prevents multi-generational human survival not because of technology, but because human biology is not adapted to this environment. The slow erosion of skeletal and muscular systems in adults combines with an untested, likely catastrophic reproductive environment. The result is a population that cannot sustain itself beyond one generation without continuous intervention, artificial gravity systems, or technological miracles that do not yet exist. Artificial solutions, like rotating habitats or centrifuge-based gravity simulators, are theoretically possible, but introduce massive engineering and logistical challenges. These systems must be enormous, continuous, and fail-safe. Any interruption, power failure, structural damage, or maintenance error would immediately expose developing fetuses and adults to partially lethal gravity, undoing all progress. Even with perfect systems, reproduction remains untested. Every embryo, every gestation would be an experiment with no Earth-based precedent, and the margin for error is virtually zero. Mars gravity, in short, is a silent killer. It does not strike like radiation or storms. It does not burn or freeze. It acts slowly, invisibly, and persistently, eroding adult bodies while simultaneously creating an uninhabitable environment for reproduction. When you combine skeletal decay, cardiovascular shrinkage, muscle loss, and cognitive decline with the absolute uncertainty of fetal development, the result is unavoidable. No human population can thrive, grow, or reproduce on Mars without fundamental changes to biology or gravity itself. This is why scientists now view Mars not just as hostile, but as a biological barrier, a planet that cannot support self-sustaining human life under current conditions. The cumulative human failure on Mars. By now, the problems are clear individually, but what really kills hope for long-term human life on Mars is what happens when they all combine. Radiation, low gravity, and reproductive risk do not exist in isolation. They interact, amplify each other, and create a cascade of failures that no technology we currently possess can stop. Mars does not simply challenge humans. It erodes them at every level, from molecules to organs to generations, in ways that compound relentlessly over time. Radiation attacks the body continuously. Every particle that reaches the surface carries energy that breaks chemical bonds, damages DNA, and sparks cascades of secondary particles that spread harm far beyond the initial impact site. Even with thick shielding or underground habitats, some radiation still penetrates, and the cumulative effects over months and years are unavoidable. Cells mutate, tissues weaken, and organs begin to fail silently. Blood vessels stiffen, bone marrow slows. The immune system falters. The brain itself is subtly reshaped, with neurons shrinking, synaptic networks degrading, and cognitive processing gradually declining. On Mars, there is no relief, no seasonal pause, and no backup system. The assault never stops. Gravity compounds the problem. On Mars, humans live at only 38% of Earth's gravity. The body evolved under full gravity, and everything from bones to muscles to circulation relies on that constant load. Partial gravity slows deterioration compared to microgravity, but it does not stop it. Bones lose density, muscles atrophy, hearts shrink, blood flow patterns shift, organs slowly sag and weaken, creating a subtle but relentless structural collapse that makes every bodily system less efficient. Step by step, year by year, the human body becomes increasingly fragile. Reproduction adds another, even more decisive layer. Fertility is uncertain. Fetal development in a partial gravity is untested and likely unsafe. Blood flow, organ positioning, and hormonal regulation are all disrupted. Every embryo faces risks of circulatory failure, organ misalignment, and developmental abnormalities. Even if a live birth occurs, the child is born into the same environment, facing the same slow erosion that affected their parents, with the added burden of inherited DNA damage from continuous radiation exposure. There is no natural stabilization. There is no multi-generational adaptation. Each generation compounds the failures of the last. The interaction between radiation and partial gravity is particularly devastating. Radiation damages bone marrow, reducing the body's ability to produce healthy blood cells. Low gravity weakens bones and muscles, reducing mobility and cardiovascular function. Together, these effects make the body far less resilient to even minor stresses. Small injuries, infections, or environmental challenges can become catastrophic. Every system is linked. Damage in one area accelerates damage elsewhere. There is no redundancy. There is no escape. The psychological toll amplifies the biological one. Humans are social animals, evolved for complex interaction in dynamic environments. On Mars, isolation, confinement, and stress from failing bodies, reduced mobility, and cognitive decline will exacerbate mental health issues. Anxiety, depression, impaired decision-making, and social tension are inevitable. These mental stresses further compromise immune response, hormone regulation, and physical performance, creating another feedback loop of decline. A colony of humans on Mars would not just struggle physically, it would fail socially and psychologically, long before genetic or structural failures render survival impossible. Even advanced technology cannot fully compensate. Spacesuits, exercise rigs, and habitats can partially mitigate damage, but they cannot replicate the integrated planet-wide systems that Earth provides naturally. Artificial gravity, whether through rotation or centrifuges, introduces enormous engineering challenges and failure risks. Habitat shielding reduces some radiation, but secondary particle cascades ensure that some dose still penetrates. Medical interventions can treat symptoms, but cannot reverse cumulative cellular damage or prevent generational DNA degradation. Every fix is partial. Every solution comes with trade-offs. The planet itself is an active agent working against human survival, not a neutral stage on which humans can build resilience. When these factors converge, the conclusion is unavoidable. Mars is biologically incompatible with multi-generational human life. The cumulative effect of continuous radiation, partial gravity, and compromised reproduction creates a system in which the concept of sustainable human settlement breaks down. Colonists might survive for a few years, perhaps even decades, with extreme technological support, but each year adds irreversible damage, and the next generation would inherit a body and genome already degraded. Survival ceases to be about life. It becomes about endurance under impossible conditions with no long-term viability. Mars is not just a hostile environment. It is an environment that actively erodes every aspect of human biology over time. Each challenge, radiation, gravity, reproduction, and psychological stress, is dangerous on its own. Together, they form a cumulative, unavoidable, and scientifically measurable barrier. There is no heroic engineering workaround, no temporary shelter, no clever design that can permanently protect humans in this setting. The planet itself ensures that multi-generational survival remains outside the realm of possibility with current biology and technology. And that is why scientists now speak in stark terms. Humans can visit Mars. Humans can work on Mars. Humans may even live there temporarily, for months or a few years, if they are willing to accept extreme, continuous risk. But Mars will never be a self-sustaining home. It will never produce children who can thrive naturally. It will never support a society in which life continues safely across generations. The planet is not hostile because it chooses to be. It is hostile because its fundamental physics and biology work against the human body at every level, in every system, and across every generation. Mars is a planet that promises adventure, exploration, and discovery, but it also delivers a hard, unyielding truth. When it comes to human survival, the odds are absolute, and they are uncompromising. For now, Mars remains a world for the brave, but not a home for humanity. The atmosphere will kill you even indoors. When we think of Mars, we imagine red landscapes, rocky plains, and maybe a shiny colony domed under the sun. What we rarely imagine is that the very air inside those habitats could be more dangerous than the storms outside. Mars's atmosphere is not just thin, it is nearly non-existent compared to Earth. Surface pressure on the red planet is less than 1% of what we experience at sea level. That might sound like a number, but the implications are immediate and unavoidable. Human bodies are designed to live at pressures of roughly 101 kilopascals. Reduce that pressure by 99%, and our lungs, blood, and tissues start failing in ways that cannot be engineered away. Even if you are safely inside a sealed habitat, the air itself must be artificially pressurized to Earth-like levels, and the margin for error is razor thin. Oxygen, a gas that sustains every heartbeat on Earth, becomes a double-edged sword under artificial pressure. High concentrations of oxygen are toxic over time, producing oxidative stress that damages lungs, eyes, and even neural tissue. Mars habitats cannot simply pack in more oxygen to compensate for leaks or system failures without creating new hazards. Fire behavior also changes dramatically. Flames burn faster, hotter, and unpredictably in low-pressure, high-oxygen environments. A minor spark in a habitat that is both sealed and artificially pressurized could ignite a catastrophic fire, leaving residents with almost no way to escape. Even the simplest human error, a drop tool, an overheating circuit, a mismanaged oxygen valve, can instantly escalate into fatal conditions that engineers cannot fully control. The atmosphere outside is equally unrelenting, and it invades human tissues in invisible ways. Nitrogen, a largely inert component of Earth's atmosphere, helps maintain proper pressure inside our cells and tissues. At Mars's surface pressure, nitrogen begins to leave human tissues, causing bubbles in the bloodstream, joint pain, and decompression sickness if rapid exposure occurs. A small leak in a habitat is not just inconvenient, it is instantly fatal. Unlike water, air can escape quickly, and humans cannot survive even minutes of exposure to Martian vacuum. Any breach in a city-scale habitat, no matter how well designed, would create a rapid decompression event far more deadly than any storm, radiation spike, or mechanical failure outside. Mars is a planet where pressure governs life more directly than temperature or radiation. The very physics of the atmosphere makes survival precarious. Even inside domes and habitats, humans are one small system failure away from instant death. Engineers can design redundancies, backup oxygen supplies, and multiple containment layers, but the margin is microscopic compared to Earth normal conditions. Every sealed room is effectively a miniature death trap unless every system functions flawlessly at all times. The consequences of error are absolute because biology cannot tolerate partial solutions when pressure drops to near vacuum levels. Even routine activities, breathing, cooking, working with machinery, carry a different level of danger. Oxygen-rich, low-pressure air is inherently unstable. Fire suppression systems, electrical insulation, and air circulation must all be meticulously calibrated. Small misalignments can produce cascading failures. On Earth, humans tolerate minor mistakes with near-zero risk. On Mars, minor mistakes can be lethal within seconds. For a habitat containing hundreds or thousands of people, even with redundancy, the statistical probability of catastrophic failure over decades becomes non-negligible. Humans may survive short periods indoors with artificial air, but the reality of living continuously in such a fragile environment is harsh, unforgiving, and unavoidable. Mars's atmosphere is not just a backdrop, it is an active, omnipresent threat. It strips away our safety margins, forces constant vigilance, and creates an environment in which even the most carefully designed habitats exist on the knife's edge. Every leak, every pressure fluctuation, every miscalculation can instantly translate into death. This is the invisible killer of Mars, one that strikes not with fire, dust, or radiation, but with the very air or lack thereof that surrounds the planet. Why sealed cities are statistical death traps over decades. Imagine a city on Mars, fully sealed under massive domes, with life support systems humming, oxygen tanks stocked, and artificial gravity machines keeping people upright. At first glance, it seems safe. It seems like humanity has finally conquered the red planet. But even in this idealized city, the numbers tell a different story. Every sealed habitat is a complex, interdependent system where physics, chemistry, and biology are working against life at every turn. The longer humans try to live there, the more the odds of catastrophic failure accumulate. Over decades, those odds are not just high. They become inevitable. The problem starts with redundancy and scale. On Earth, the atmosphere is a constant buffer. Leaks, fires or minor errors are absorbed by sheer volume of air and pressure, giving humans time to respond. On Mars, every habitat is essentially a contained bubble with no natural backup. A leak in a single module reduces pressure incrementally, changes oxygen concentrations, and stresses environmental control systems. The longer the city exists, the more opportunities there are for failures in plumbing, valves, sensors, or structural seals. Each failure may be small, but the probability of at least one fatal incident grows steadily with time. Over decades, even a city designed to perfection cannot avoid cumulative risk. Engineers can never eliminate human error, material fatigue, or unpredictable environmental stresses completely. The air itself becomes a persistent hazard. Maintaining Earth-like pressure and oxygen levels in a sealed habitat requires continuous monitoring and correction. Oxygen concentrations must be high enough to support life, but low enough to prevent toxicity. Carbon dioxide must be scrubbed efficiently. Trace gases and contaminants from human metabolism or industrial activity must be filtered constantly. A minor malfunction in any of these systems can lead to hypoxia, hyperoxia, or toxic gas buildup. Even sophisticated sensors and automatic controls have reaction times and failure probabilities. Over years and decades, these probabilities compound. In statistics, this is called cumulative risk. The longer a system operates under imperfect conditions, the more likely it is to fail catastrophically. In a Mars habitat, failure does not mean inconvenience. It means instant or near-instant death. Fire risk is another constant threat. On Earth, flames behave predictably because atmospheric pressure is stable and oxygen levels are balanced. On Mars, sealed habitats often require elevated oxygen concentrations to compensate for thin atmospheric pressure outside, which makes fires burn hotter, spread faster, and become far more destructive. In a sealed city, even a single spark, electrical equipment, a cooking accident, or chemical reaction can ignite a chain reaction with deadly consequences. Fire suppression is complicated by low pressure and limited water supplies. Unlike Earth, where fire can be vented or contained, a habitat fire on Mars cannot be escaped easily. The inhabitants are trapped inside a high-risk environment, and over decades, the statistical likelihood of one catastrophic fire grows towards certainty. The structural integrity of sealed cities is another ticking clock. Domes and modules are built to withstand external pressures, dust storms, and occasional meteorite impacts. But no material lasts forever. Plastic polymers degrade under constant UV radiation. Metals fatigue under repeated thermal expansion, and seals slowly lose elasticity. Micrometeoroid impacts, tiny punctures invisible to the naked eye, can weaken the structure incrementally. Over decades, these cumulative effects make catastrophic failure increasingly probable. Each layer of redundancy buys time but does not eliminate risk. Eventually, the odds reach a point where a single, unforeseen event can compromise an entire habitat. Then, there's the human factor. In sealed cities, humans generate waste, heat, and contaminants. Every activity, breathing, cooking, sanitation, industrial work, adds pressure to the life support system. Systems must be maintained constantly, and errors or oversights accumulate over generations. Fatigue, miscommunication, and human error cannot be engineered away. Every year, every new resident adds to the statistical probability of a failure that cannot be repaired fast enough. A habitat designed to survive a single generation may become impossible to maintain across multiple decades. Even if these systems are perfect, radiation and gravity remain silent, inexorable threats. High-energy cosmic rays penetrate habitats, gradually degrading DNA and increasing the risk of cancer, organ failure, and cognitive decline. Low gravity or partial gravity erodes bones, muscles, and the cardiovascular system. These biological stresses interact with the habitat environment. Weakened humans are less able to maintain critical life support systems, respond to emergencies, or repair damage. The statistical probability of catastrophic failure is no longer just mechanical, it is biological. Every decade increases the likelihood that human systems themselves fail, either through accumulated injury, illness, or error. This is why scientists describe Mars' sealed cities as statistical death traps. The planet does not have to actively kill people, it simply sets up a situation where cumulative risk, structural, chemical, biological, and operational, inevitably intersects with human fragility. Over decades, redundancy fails, humans falter, systems degrade, and the habitat itself becomes the environment of inevitable catastrophe. It is not about bravery, technology, or ingenuity. It is about numbers, probabilities, and the hard laws of physics and biology. Mars cannot sustain life indefinitely, not even in sealed, engineered cities, because over time, the cumulative effect of every hazard adds up to certain failure. Mars is a world where even life inside protective bubbles cannot escape the relentless mathematics of risk. Every sealed city is a fragile island in a sea of unbreathable air, extreme pressure differentials, and invisible killers, where the longer you live, the closer you come to the inevitable. That is the inescapable truth about life on the red planet. The atmosphere is not just thin, it is lethal, and no city, however sealed, can escape the statistical laws that make survival over decades impossible. Mars dust, the invisible biological threat. Mars is often painted as a barren, windswept desert, red horizons, sweeping dust storms, and endless plains. But there is a threat hiding in plain sight, one that is invisible to the eye, yet far more dangerous than any storm or radiation burst. Mars dust. This is not ordinary dirt. It is a relentless, microscopic hazard that can infiltrate every part of a human habitat, every corner of a spacesuit, every breath a colonist takes, and its impact on biology is profound and largely untreatable. To understand why, we need to look closely at what Mars dust is, how it behaves, and how it interacts with human systems over time. The composition of Mars dust is uniquely dangerous. It is loaded with perchlorates, salts that are highly reactive and toxic to humans. On Earth, perchlorates are used in rocket fuel, explosives, and even fertilizers, and exposure is carefully controlled. On Mars, these chemicals are spread across the surface in dust and sand that settles on every surface and drifts through the air. Inhaling even tiny amounts of perchlorates disrupts thyroid function, interfering with hormone production, metabolism, and organ regulation. The effect is subtle at first, slight fatigue, minor metabolic imbalances, but over months and years the cumulative impact becomes significant, leaving humans chronically weakened, less resilient, and more vulnerable to disease. In addition to chemical toxicity, Mars dust is composed of fine silica particles, often smaller than a micron in diameter. These particles behave like microscopic shards that embed themselves deep into lung tissue, causing inflammation, fibrosis, and long-term respiratory damage. On Earth, industrial workers exposed to silica develop silicosis over years, even decades. On Mars, the risk is magnified. Microgravity and partial gravity prevent natural clearing of lungs and cilia function, so inhaled dust settles more persistently, irritating tissue and reducing respiratory efficiency. Colonists may appear healthy, but internally their lungs are slowly stiffening, blood oxygen exchange is gradually reduced, and susceptibility to infection rises. Every breath of Martian air carries this risk, and no filtration system can remove it entirely, because dust is both fine enough to penetrate filters and pervasive enough to infiltrate even sealed habitats. Dust on Mars is not passive. It carries a significant electrostatic charge that makes it stick to every surface. Spacesuits, gloves, helmets and equipment are coated with dust after every excursion. Dust infiltrates habitat air systems, moving unseen through ducts and vents, contaminating the very air meant to sustain life. Electronics are compromised as well. Circuit boards and sensors are gradually eroded, short-circuited or blocked, creating silent failures that are difficult to diagnose and even harder to repair. The dust is relentless. It cannot be washed away with ordinary water. It cannot be neutralized by magnets or static fields. Every solution tested in labs on Earth has only partially mitigated its spread, and all measures require constant maintenance and vigilance. Over time, the dust will always find a way inside, and inside is where it does its most insidious work. The biological consequences extend beyond lungs and thyroid. Mars dust also contributes to immune suppression. Continuous inhalation of fine particles, combined with low gravity and radiation stress, keeps the immune system in a chronically activated yet inefficient state. White blood cells are overworked, inflammatory pathways are constantly triggered, and tissue repair slows. This creates a perfect storm for opportunistic infections, slower recovery from injuries, and reduced effectiveness of vaccinations or treatments. On Mars, where medical facilities are limited and resources scarce, even minor infections can become life-threatening. The dust transforms the body from a resilient system into a fragile one, where minor stresses accumulate into systemic failures. Worse still, the dust infiltrates habitats even when humans are not directly exposed. Air circulation systems draw it in, filters clog but cannot stop every particle, and surfaces must be continuously cleaned, an impossible task over years. Every suit, every glove, every helmet that returns from an outside excursion brings a fresh load inside. Human activity, even normal walking or moving equipment, suspends dust back into the air, creating a self-perpetuating cycle. In this way, the dust is not a static environmental hazard. It is a dynamic, unrelenting threat that interacts with every human system and every technological support system on the planet. There is currently no known long-term mitigation method for Mars dust. Even the most advanced filtration, cleaning and habitat design proposals can only reduce exposure, not eliminate it. Dust will infiltrate, it will irritate, it will chemically react, it will silently degrade human health, electronics and structural integrity over months and years. It is invisible, persistent and unstoppable in any practical sense. Mars dust is the ultimate silent killer. It does not burn or strike. It does not freeze or crush. It spreads imperceptibly, silently attacking biology at the cellular level, weakening humans over time, and slowly eroding the very systems designed to keep them alive. In every breath, every surface and every piece of technology, Mars dust enforces the harshest of limits, that the planet, despite its allure and apparent accessibility, remains fundamentally hostile to human survival. It is an invisible enemy, pervasive and patient, and it underscores a truth that no spacesuit, habitat or engineering solution can fully overcome. On Mars, the air itself is a threat, and living among the dust is a battle humans were never evolved to win. Food, soil, and the nutrient collapse problem. When we imagine a Mars colony, we imagine lush hydroponic farms inside gleaming domes, rows of green vegetables under artificial lights, and the promise of self-sustaining food. But the reality is far harsher. The Martian surface, often called regolith, is not soil in any sense that humans can use for growing food. Earth soil is a living system, rich with microorganisms that decompose organic matter, fix nitrogen, recycle nutrients, and create the complex fertile matrix in which plants thrive. Mars' regolith is sterile, inert, and hostile. It is packed with toxic salts, including perchlorates, that interfere with plant metabolism and make unprocessed regolith unsafe for human consumption. Even if plants could survive in Martian dust, those same salts leach into their tissues, carrying chemical toxicity that accumulates in the human body. But the challenges go beyond chemical toxicity. Soil is not just dirt, it is a living ecosystem. Microbes in the soil form symbiotic relationships with plants, regulating growth, enhancing nutrient uptake, and protecting roots from disease. On Mars, these microbial networks do not exist. Attempts to simulate them in controlled environments on Earth are limited and fragile. When you try to recreate these ecosystems artificially, they are extremely sensitive to small changes in temperature, moisture, and chemical composition. Any fluctuation can collapse the system, and in the Martian environment, fluctuations are inevitable. A greenhouse might appear lush at first, but without the self-replenishing microbial network of Earth soil, nutrient availability declines steadily, plants weaken, and food quality diminishes. Even hydroponics, often touted as a solution, cannot fully compensate for these biological gaps. Plants grown in liquid nutrient solutions can survive, but scaling hydroponics to feed a full human colony is biologically precarious. Nutrient solutions degrade over time, microbial imbalances develop, and trace mineral deficiencies accumulate silently. The moment a nutrient imbalance occurs, plant growth slows, vitamin and mineral density drops, and crops fail to meet human dietary requirements. Unlike Earth, where soil buffers these imbalances and natural cycles replenish nutrients, Mars offers no such safety net. The colony becomes entirely dependent on precise, perfectly maintained artificial inputs, and even minor deviations can propagate into serious nutritional deficiencies. The problem extends further into the human gut. Humans rely on the gut microbiome not only to digest food, but to synthesize essential vitamins, regulate the immune system, and maintain metabolic health. Spaceflight studies have shown that microgravity, radiation, and sterile diets degrade gut microbiota over time. Colonists relying solely on hydroponic crops would face compounded microbial stress. Sterile diets reduce beneficial bacteria, and nutrient-dense foods degrade over time, leaving the microbiome unable to support human physiology fully. Immune suppression, metabolic disorders, and gastrointestinal illnesses would slowly become endemic in any Martian population. Even if the colony survives the first months with hydroponic food, the nutrient density collapses over time. Vitamins like B12, C, and K degrade faster in controlled artificial systems, while trace minerals become locked in chemical forms unavailable to humans. Crops grown hydroponically may appear green and healthy, but the essential nutrients that prevent scurvy, anemia, and long-term organ degeneration gradually vanish. The result is an invisible starvation. Humans are fed, but their bodies are slowly robbed of the nutrients needed to maintain bone strength, cognitive function, reproductive health, and immune resilience. Over years, this slowly accumulates into systemic physiological decline. Mars is not just a desert in terms of land, it is a desert in terms of biology. The regolith cannot be used directly, hydroponics cannot replace the lost microbial networks, and human physiology itself begins to degrade from insufficient nutrient input. What looks like a thriving green colony on the surface is, beneath the lights, a system slowly unraveling at the cellular level. Every hydroponic tray, every recycled nutrient solution, every controlled harvest carries within it the seeds of collapse. Nutrient density, microbial support, and biological resilience are not simply engineering problems. They are fundamental limits imposed by the Martian environment. Mars offers no soil, no microbial buffer, and no natural cycle to support long-term human nutrition. In a colony dependent on artificial systems, every day compounds these vulnerabilities. Every crop grown artificially begins a slow decline in nutrient value, and every human relying on those crops experiences a gradual erosion of health. What appears to be survival is, in reality, a slow, unavoidable biological collapse, one that no number of greenhouses or hydroponic vats can fully prevent. Mars is a planet that will never nourish humans in the way Earth does, and the moment the first generation tries to feed itself independently, the cracks begin to appear. Why hydroponics don't scale biologically? Even if a Mars colony manages to grow crops in hydroponic systems or artificial greenhouses, the challenges extend far beyond the plants themselves. Scaling hydroponics to sustain a full human population over years or decades is not just an engineering problem. It is a biological problem that becomes progressively worse with time, a problem that undermines the very foundation of human survival. Hydroponic crops require perfectly balanced nutrient solutions, precisely controlled water and pH levels, artificial lighting calibrated to mimic sunlight, and constant oversight to prevent microbial contamination. On Earth, these factors are manageable at small scales, but on Mars, where every system operates in isolation from natural ecosystems, even minor deviations cascade into significant failures. Nutrient cycles are fragile. Trace minerals degrade over time, and the very plants humans rely on begin to lose their capacity to nourish. A single miscalculation in a nutrient formula or a delay in maintenance can start a chain reaction that results in crops producing less food with lower vitamin and mineral density, threatening human health in ways that are invisible at first glance. Human biology compounds this problem. Microgravity, radiation exposure, and sterile diets experienced during extended space travel have shown that the gut microbiome, a critical network of bacteria, fungi, and viruses that maintain digestion, immunity, and metabolic health, degrades over time. Even on Earth, diet plays a dominant role in shaping the microbiome. On Mars, where food comes almost entirely from hydroponics or carefully recycled systems, the lack of natural microbial diversity in crops accelerates the loss of gut flora. Over months, beneficial microbes diminish, leaving the digestive system weaker, nutrient absorption less efficient, and immunity chronically impaired. A Martian colonist could eat what appears to be a complete diet, yet their body may be unable to extract the full spectrum of nutrients required for long-term health. This is not hypothetical. Spaceflight research confirms that astronauts experience measurable declines in gut diversity and function even over periods as short as 6 months. The nutrient problem is not only microbial, it is chemical. Hydroponic systems, no matter how carefully designed, cannot perfectly replicate the complex soil chemistry that naturally provides vitamins, trace minerals, and cofactors. Over time, essential micronutrients such as magnesium, selenium, zinc, iodine, and vitamin K become depleted in the water-based systems, especially when crops are grown continuously without a biological soil buffer to recycle nutrients. Vitamins like C and B12 degrade in artificial systems faster than in natural soil, and many minerals are present in forms that humans cannot efficiently absorb. The crops may look vibrant and healthy, but their nutrient density collapses silently, leaving humans vulnerable to anemia, scurvy, weakened bones, cognitive deficits, and impaired reproduction. Every month, every harvest, the colony slowly consumes itself from within, not due to starvation of calories, but starvation of essential biology. As hydroponics scales up, maintenance becomes exponentially more complex. Nutrient solutions must be constantly monitored, purified, and replenished. Pumps, reservoirs, filters, and sensors are mechanical systems that can fail, often unpredictably. On Earth, Such failures are inconvenient. On Mars, they become life-threatening. A minor pump failure can change nutrient concentrations, subtly reducing plant health, which over weeks or months reduces crop yields and nutrient quality. The more humans depend on these systems, the greater the cumulative risk. Every human meal becomes a calculated gamble against biological and mechanical failure. And over decades, the statistical likelihood of nutrient collapse approaches certainty. The colony may appear to be thriving, but internally, the population is slowly losing the ability to sustain itself, both physically and biologically. This biological fragility extends to reproduction. Humans depend on nutrient-rich diets to support healthy pregnancies, fetal development, and long-term health. On Mars, even a perfectly maintained hydroponic farm cannot reliably provide the full spectrum of nutrients required to ensure multi-generational survival. Deficiencies in iodine, folate, selenium, or vitamins B12 and D can cause irreversible developmental defects in children, weaken adult immunity, and accelerate the degeneration of bone, muscle, and cardiovascular systems. The collapse of nutrient density in artificial food systems creates a situation where colonists might survive for a few years, but the next generation is biologically compromised before birth. Reproduction becomes a gamble with no margin for error. The combination of hydroponic fragility and microbiome degradation creates a feedback loop. Weak crops lead to weaker humans. Weaker humans struggle to maintain the nutrient system, and the resulting biological decline further reduces the colony's capacity to correct failures. Every day in this artificial ecosystem becomes a battle against invisible, cumulative decay. On Mars, human bodies and artificial agriculture are trapped in a continuous, mutually reinforcing cycle of slow deterioration, where time is the enemy and even the most advanced technology can only slow, not prevent, the inevitable collapse. Mars may offer oxygen, water, and sunlight in controlled habitats, but it cannot provide the natural systems that underpin human nutrition and microbiology. Hydroponics is a stopgap, not a solution. Over months and years, the invisible collapse of nutrient density and microbial health undermines every aspect of human survival: strength, immunity, cognition, reproduction, and longevity. A colony that appears to be thriving is, in truth, walking on the edge of a slow biological cliff, and with every year that passes, the edge becomes closer, sharper, and more unavoidable. On Mars, no artificial greenhouses, hydroponic vats, or recycled nutrient solutions can fully replace the complex, living, self-sustaining ecosystems that Earth evolved over billions of years. Humans are left to eat, breathe, and live on systems that are inherently temporary, fragile, and biologically insufficient, with consequences that will compound silently, inevitably, and lethally. Water is not the solution. People think it is. Water is often portrayed as the ultimate solution for colonizing Mars. It's the first resource people imagine when they think of survival. Melt ice, drink, grow crops, and suddenly life becomes possible. But the reality is far harsher. Water on Mars exists mostly in the form of ice, buried under regolith, locked in polar caps, or frozen in scattered subsurface layers. There are hints of briny liquid water in some underground pockets, but these are highly saline, acidic, and toxic to humans and plants alike. The extraction of water is not a simple matter of scooping it up. It requires enormous energy to drill, heat, and purify even small quantities. Every litre harvested from ice or brines comes at a massive cost in power, infrastructure, and labour, and the yields are far lower than the consumption rates required to sustain a human population over years, let alone decades. Even when water is successfully extracted, it is rarely safe to drink or use for agriculture without complex treatment. Martian ice and brines contain perchlorates, heavy metals, and other chemical contaminants that cannot simply be filtered out with conventional systems. Brine water is often supersaturated with salts that are lethal to humans and plants, requiring multi-step purification to become even marginally usable. Every system must constantly monitor chemical composition, pH, and microbial contamination, because even microscopic errors can result in toxic water entering habitats or hydroponic farms. Water, in this context, is not a freely available life source. It is a fragile, high-maintenance resource that can become deadly with a single malfunction. Recycling water is also far from a perfect solution. Closed-loop water systems, like those used on the International Space Station, work over months or a few years, but their biological efficiency declines over time. Microbes, biofilms, and chemical residues accumulate in filtration systems, slowly degrading water quality. Trace chemicals leach from piping and storage containers, adding unseen contaminants that human bodies must process. Over years, even carefully monitored recycled water becomes less reliable as a nutrient source for plants and a safe fluid for humans. The longer a colony operates, the more the water system itself becomes a source of biological stress rather than a solution. Small deviations in water quality compound over time, subtly affecting metabolism, organ function, and immune health, often long before anyone notices. The scarcity and instability of Mars water have cascading consequences for survival. Agriculture, hygiene, industrial processes, and even oxygen production all depend on reliable water. A minor disruption in extraction, contamination, or recycling can ripple across the colony, reducing crop yields, compromising hygiene, and stressing human physiology. The illusion of abundant water is seductive. Ice can be seen, brines can be detected, but perception does not equal practicality. Mars water is not a natural reservoir waiting to be tapped. It is a tightly controlled, fragile resource whose availability and safety are constantly at risk. Ultimately, the promise of water as a lifeline is limited by biology itself. Even with perfect extraction and purification, human bodies require consistency. Variations in mineral content, trace contaminants, or microbial load slowly degrade health over years. Colonists may survive initial months, but over decades, cumulative effects on kidneys, cardiovascular systems, and immune function begin to appear. Closed-loop water systems, no matter how advanced, cannot replicate the naturally renewing water cycles of Earth. They are temporary fixes for a fundamentally unsupportive environment, and over time, this limitation becomes one of the most intractable barriers to multi-generational survival. On Mars, water is neither plentiful nor simple. It is a high-cost, chemically hazardous, and biologically fragile resource. The very systems designed to make it usable, drills, heaters, filters, recycling loops, cannot operate perfectly forever. Every year adds a subtle layer of risk. Every malfunction, contamination, or inefficiency weakens the colony. For humans dreaming of self-sustaining life, water is not salvation. It is a constant, invisible, and ultimately inescapable threat that defines the narrow margin between survival and failure. Psychology is not the main problem. Biology is. When people imagine humans living on Mars, the first barrier that comes to mind is usually psychological: isolation, confinement, extreme environments. We picture astronauts trapped in tiny habitats, staring at red horizons for years, slowly going mad from loneliness. Movies and pop culture reinforce this image. Mental breakdowns, cabin fever, panic, despair. It's intuitive. It feels real. But decades of research in extreme Earth environments and spaceflight have repeatedly shown that human psychology is, in fact, surprisingly resilient. The real, unavoidable threat to life on Mars is not loneliness, stress, or fear. It is biology itself, and that is a far more insidious, relentless, and inescapable force. Let's start with what we know from isolation studies. Teams stationed in Antarctica, especially in remote stations like Concordia or Amundsen Scott South Pole Station, endure months of complete isolation, extreme cold, and near-permanent darkness during winter. Researchers monitor mood, cognitive function, social cohesion, and productivity closely. The results are striking. Most individuals maintain mental stability for months, and even over a full year, psychological deterioration is rare. Mood dips do occur, but they are usually mild, predictable, and mitigated by structured schedules, social cohesion, and purposeful work. These crews survive the harshest, most extreme Earth environments, psychologically intact, even when social contact with the outside world is non-existent. On the International Space Station, the data is even more compelling. Astronauts spend 6 months to a year in cramped, pressurized modules, orbiting hundreds of kilometers above the Earth. They face a hostile vacuum outside, high levels of cosmic radiation, limited food variety, and strict isolation from Earth. Despite these challenges, studies show that astronauts generally maintain cognitive function, social collaboration, and mental health at levels sufficient to complete mission objectives. Stress, conflict, and homesickness do appear, but they are predictable and manageable. Training, protocols, and rotations of duties effectively mitigate psychological risks. In other words, the human mind is remarkably adaptable to isolation and extreme environments, far more adaptable than most people realize. Loneliness is unpleasant, monotony is frustrating, but neither is a death sentence. Yet while mental resilience is possible, biology is not forgiving. Humans are biologically optimized for Earth. Every system in our bodies, musculoskeletal, cardiovascular, immune, hormonal, neurological, depends on a combination of gravity, atmospheric pressure, radiation shielding, and nutrient-rich ecosystems that Mars cannot provide. The moment you remove one of these pillars, subtle, cumulative damage begins. Unlike psychological stress, which can be countered with social strategies, structured routines, and coping mechanisms, biological degradation is relentless, invisible, and irreversible in many cases. It cannot be managed with discipline, motivation, or training. It is the silent predator lurking behind every red horizon. Take the musculoskeletal system, for example. On Earth, our bones, muscles, and connective tissues are constantly subjected to gravity, which stimulates growth and maintenance. On Mars, gravity is only 38% of Earth's, a level that the human body has never evolved to sustain. Even on the ISS, where astronauts live in near-zero gravity, studies show that bone density declines at 1 to 2% per month, muscles atrophy, and joints stiffen. Cardiovascular systems shrink as the heart does less work pumping blood in low gravity. On Mars, partial gravity may slow these effects, but it does not stop them. Over months and years, this leads to weakened bones prone to fracture, muscles incapable of supporting normal movement, and circulatory systems that fail to maintain organ function. Training, exercise, and diet can mitigate the rate of decline, but they cannot prevent the inevitable erosion. Gravity is not negotiable. Mars does not bend to human biology. Radiation presents another biological wall. Unlike the controlled shielding in Antarctic bases, or even the partial protection of Earth's atmosphere, Mars has no global magnetosphere, and its thin atmosphere provides minimal shielding from cosmic rays and solar particle events. These high-energy particles penetrate tissues, break DNA strands, and produce secondary radiation cascades inside the body. Long-term exposure accelerates cancer risk, but more insidiously, it causes central nervous system damage, cognitive decline, and neurodegeneration. The effects are cumulative and irreversible. Unlike psychological stress, Where therapy, rest, or rotation can restore mental resilience, the brain cannot repair itself after repeated high-energy particle damage. The neurons may shrink, synapses may degrade, and the risk of Alzheimer-like pathology rises dramatically. No amount of mental training, meditation, or morale-building exercises can counteract this. Biology, unlike psychology, does not bend to willpower. The immune system, which most people take for granted, is also under siege. Long-duration spaceflight and partial gravity environments show consistent patterns of immune dysregulation. T-cell function declines, inflammatory responses become erratic, and the body struggles to fight infections. On Mars, radiation, low gravity, poor diet, and environmental toxins like perchlorates in the air and dust all act in concert to weaken the immune system further. A small infection that would be trivial on Earth can become life-threatening. Unlike mental health, which can be supported with counselling, stimulation, and social interaction, immune decline is relentless and accelerates with exposure. It is cumulative, invisible, and unforgiving. Hormonal systems are similarly vulnerable. Stress hormones, reproductive hormones, thyroid function, all of these begin to falter under Mars conditions. Low gravity changes hormone feedback loops, radiation interferes with cellular signaling, and nutrient-depleted diets exacerbate deficiencies. Over months, hormonal imbalance disrupts metabolism, reproduction, bone health, cardiovascular function, and mood. Again, psychological resilience does little to mitigate this. The body is not just experiencing stress, it is being physically rewired in ways that are incompatible with survival over generations. Perhaps most devastating of all is reproduction itself. Humans have never reproduced in partial gravity or under continuous radiation exposure. Animal studies in microgravity suggest developmental abnormalities, miscarriages, and organ malformations. Mars presents the same problem, but magnified. Even if adults survive for decades, multi-generational survival is biologically impossible without protective measures that do not yet exist. The planet's conditions actively prevent the continuation of human life beyond a single generation. Psychology cannot overcome this. Biology cannot negotiate with probability. Humans are trapped within limits they did not evolve to transcend. What makes this threat even more insidious is its invisibility. Psychological stress manifests outwardly: anxiety, irritability, insomnia. Humans can recognize and correct it with interventions. Biological deterioration, however, is subtle. Bone density declines silently. Immune function falters without symptoms. Organs weaken while outward performance remains normal, and DNA damage accumulates over years. Colonists might believe they are healthy, fully functional, and capable of surviving, when in reality, every system in their bodies is gradually losing the capacity to maintain life. The difference is stark. Mental health can be trained, supported, and corrected. Biology cannot. This is why focusing on psychology as the primary barrier to Mars colonization is misleading. Training, resilience building, and social structures can indeed allow humans to cope with isolation, monotony, and stress. History and spaceflight demonstrate that humans are remarkably adaptable in these areas. What cannot be trained away, mitigated with social engineering, or solved with willpower is biological fragility. Every organ, every system, every cellular mechanism works in a delicate balance on Earth. Mars disrupts that balance across the board. Bones weaken, muscles atrophy, hearts shrink, blood vessels stiffen, neurons degrade, hormones collapse, immune function fails. All of these effects interact, amplifying each other, producing cascading physiological decline that no amount of psychological support can halt. No amount of training stops. When you remove the illusion of psychological barriers on Mars, what remains is the cold, relentless truth of biology. Unlike mental stress, which humans can adapt to, Long-term exposure to the Martian environment systematically attacks the very systems that allow humans to survive. And unlike mechanical or engineering problems, there is no manual, no training regimen, no social structure that can protect the body from the combined assaults of radiation, gravity deficits, and chemical stresses. Every organ, every cell, every physiological feedback loop is under siege in ways that accumulate silently over time, often imperceptibly, until collapse is inevitable. Radiation is the most insidious of these threats. On Earth, our magnetic field and thick atmosphere shield us from the constant bombardment of cosmic rays and high-energy solar particles. On Mars, that shield no longer exists. The planet lost its global magnetosphere billions of years ago, and its thin atmosphere provides only a fraction of the protection Earth gives us. Surface radiation measurements from orbiters and rovers have confirmed exposure levels roughly 40 to 50 times higher than Earth's surface. It is not a matter of occasional danger, it is a constant, invisible storm. High-energy particles penetrate tissues, interact with atoms, and produce secondary particle cascades, including neutrons, protons, and electrons. These particles smash through DNA, breaking strands, creating mutations, and producing irreparable cellular damage. No amount of protective gear or habitat shielding can fully block these particles, because they generate secondary radiation inside the very materials meant to protect you. Every day on the Martian surface is a biological gamble, with probabilities that increase steadily over months and years. The brain is particularly vulnerable. Long-duration exposure to high-energy radiation has been shown in animal models to cause neurodegeneration, synapse loss, and cognitive decline. Neurons shrink, synaptic connections falter, and the risk of Alzheimer-like pathology rises sharply. Astronaut studies from ISS missions show subtle cognitive impairments from long-term microgravity and low-level radiation exposure. But Mars magnifies these risks many-fold. Tasks that require attention, memory, and coordination slowly deteriorate over time, creating a feedback loop. As the brain weakens, it becomes less capable of managing the very systems required for survival, including monitoring habitat integrity, hydroponic health, or radiation exposure itself. Unlike mental stress, this decline is not psychological. It is structural and irreversible, and no meditation, motivation, or morale-building exercise can prevent it. Radiation also attacks hormonal systems with equal relentlessness. Endocrine glands, the thyroid, adrenal glands, and pituitary, are exquisitely sensitive to ionizing radiation. Even low doses disrupt signaling, creating cascading failures across metabolism, stress response, and reproductive health. Cortisol cycles falter, leaving humans vulnerable to chronic inflammation and cardiovascular strain. Thyroid hormones become unstable, affecting energy production, brain function, and organ efficiency. Sex hormones decline, fertility diminishes, and pregnancy becomes increasingly dangerous or biologically impossible. On Earth, these systems operate in an environment finely tuned over millions of years. Mars disrupts every balance. No training regimen, exercise protocol, or psychological intervention can restore a hormone once its production cycles are irreversibly impaired. Biology cannot be coached, reasoned with, or motivated. It simply deteriorates. The immune system is the final, and perhaps most critical, line of defense, and it too fails under Mars's conditions. Ionizing radiation damages bone marrow, the source of stem cells that generate white blood cells. Over time, this results in immune suppression, delayed pathogen response, and systemic vulnerability. Microgravity and poor nutrition exacerbate the decline. On Earth, a minor infection is managed almost instinctively. On Mars, the same pathogen could become lethal. Closed habitats, recycling air and water make matters worse. Even the tiniest contamination event can trigger outbreaks, and the weakened immune systems of colonists cannot contain them. Vaccinations may offer partial protection, but cumulative radiation damage gradually reduces the effectiveness of the adaptive immune system itself. Over years, what starts as a functional defense becomes a fragile, crumbling system, unable to respond to threats that Earth humans would face with ease. The interaction between these biological threats amplifies their impact. Radiation damages DNA, which weakens tissues and disrupts organ function. Hormonal collapse accelerates musculoskeletal and cardiovascular deterioration. Immune suppression leaves the body vulnerable to infection, which stresses an already compromised system. Cognitive decline reduces the ability to respond to emergencies, manage complex life support systems, and maintain personal and environmental health. Every system in the human body interacts, and when multiple systems fail simultaneously, the result is cascading physiological collapse, a process that cannot be slowed by training, motivation, or ingenuity. Reproduction is particularly vulnerable to these biological assaults. Radiation-induced mutations accumulate in germ cells, increasing the risk of miscarriage, congenital defects, and long-term organ malformations in offspring. Hormonal imbalances affect fertility, while nutrient-poor diets and compromised microbiomes further reduce the likelihood of healthy pregnancy. Mars, for all its apparent potential, is not a planet where humans can reproduce safely. No psychological training, no preparation, no motivation can overcome the fundamental environmental constraints that prevent multi-generational survival. Biology imposes a hard ceiling. Humans may survive temporarily, but they cannot thrive, and they cannot extend life across generations. Even with the most advanced life support systems, habitats, or artificial protection, these biological failures continue invisibly. Colonists may appear functional, capable of work and social interaction, fully engaged in exploration or research. Yet beneath the surface, neurons are dying, immune defenses are weakening, hormonal cycles are collapsing, and DNA damage is accumulating in ways that will eventually manifest as organ failure, systemic disease, or fatal infection. Unlike psychological stress, which can be monitored, corrected, and trained against, biological decline is insidious, cumulative, and irreversible. It is a slow-moving storm that eventually overwhelms even the most prepared and disciplined individuals. This is the ultimate barrier to long-term human survival on Mars. Engineering solutions, radiation shelters, exercise regimens, nutrient supplementation, artificial gravity experiments can slow the rate of decline, but they cannot stop it entirely. Biology is not a problem to be engineered away. It is a law that cannot be violated. The body simply cannot function indefinitely in a Martian environment without catastrophic consequences. The very systems that make life possible on Earth, immune, endocrine, nervous, reproductive, cardiovascular, are designed for a planet with thick atmosphere, strong gravity, natural radiation shielding, fertile soil, and a rich ecosystem. Remove any of these pillars, and the entire structure begins to fail. On Mars, every single one of these pillars is missing, compromised, or insufficient. No training, no preparation, no psychological resilience can substitute for the fundamental support that the Earth provides. Mars is biologically hostile. Radiation penetrates tissues, destroying DNA and neurons. Hormones falter and fail. The immune system collapses under stress. Fertility is compromised, and every system amplifies the failure of the others. Unlike psychological stress, which can be managed, the biological assault is inescapable, cumulative, and eventually fatal. A human might survive for months or even a few years, but multi-year habitation, let alone multi-generational colonization, is biologically impossible. The mind may persist, but the body will not. On Mars, psychology is a red herring, a distraction from the true, unavoidable enemy: biology itself. The grim reality is this: no amount of training, preparation, social support, or mental fortitude can prevent radiation-induced neurodegeneration, hormonal collapse, and immune failure. Mars does not negotiate, and it does not forgive. Humans can dream, explore, and survive temporarily, but the laws of biology dictate that long-term survival is not just improbable, it is impossible. Every red horizon hides this truth. Every icy deposit, every sealed habitat, every hydroponic farm is a temporary buffer against a relentless biological countdown. The planet itself does not need to actively kill you. Its conditions are already sufficient to ensure that over time, human bodies cannot endure, cannot adapt, and cannot persist. On Mars, no training regimen, no motivational speech, and no disciplined crew schedule will ever compensate for the slow, invisible, inexorable assault of radiation, hormonal collapse, and immune system failure. Biology, not psychology, is the true and ultimate limit to human survival, and it is a limit that Mars enforces with absolute certainty. Why terraforming Mars is scientifically impossible. When we think about colonizing Mars, the idea of terraforming, the grand vision of turning the red planet into a blue and green echo of Earth, often looms large. It is a compelling dream, an atmosphere thick enough to breathe, weather cycles like Earth's, oceans, rivers, maybe even clouds drifting over mountains. But this dream is not science, it is imagination. The reality is stark, unforgiving, and grounded in physics. Mars is not Earth, and no known process can transform it within any meaningful time frame for human survival. To begin with, Mars simply does not have enough atmosphere. Earth's atmosphere, which sustains life, weighs roughly 5 times 10 to the 18th power kilograms. To give Mars even a fraction of that protective envelope, enough to support liquid water on the surface or shield against cosmic radiation, we would need to multiply its current atmosphere by hundreds of times. Mars's atmosphere is incredibly thin, less than 1% of Earth's surface pressure, composed mostly of carbon dioxide, with only trace amounts of oxygen and nitrogen. To achieve Earth-like conditions, we would have to generate a staggering mass of gas and deliver it to the surface, not in the form of temporary vapor, but as a stable, self-sustaining atmosphere capable of resisting the solar wind that strips gas away. The numbers are staggering. Even if every ounce of CO2 frozen in the polar caps and subsurface layers were released, Mars would still fall far short of a breathable, pressurized environment. The scale of the problem is not small, it is astronomical. Adding atmosphere is only half the challenge. Mars lacks a magnetic field, which is critical to retaining that atmosphere over long periods. Earth's magnetic field, generated by a molten convecting iron core, deflects high-energy particles from the Sun and prevents the atmosphere from being gradually eroded into space. Mars's core cooled billions of years ago, and with it, its global magnetic field disappeared. Without this shield, any atmosphere we artificially generate will slowly leak into space. Estimates suggest that the solar wind could strip away an artificially thickened atmosphere over tens of thousands to millions of years. To restart a global magnetic field, we would need to inject colossal amounts of energy, more energy than humanity can realistically generate for thousands of years. And we have no technology capable of reigniting a planetary dynamo in a dead, slow cooling core. This is not an engineering problem. It is a geophysical impossibility with current knowledge. The planet itself cannot be coerced into Earth-like behavior. Some proposals for terraforming rely on dramatic interventions, like nuking the polar ice caps to release CO2 and water vapor into the atmosphere. At first glance, it seems simple. Melt the ice, thicken the atmosphere, warm the planet. But physics quickly disproves this optimism. The polar ice caps contain only a fraction of the CO2 required to achieve significant atmospheric pressure, and much of the released gas would escape into space over time. Even worse, the resulting water vapor would condense and freeze again in a cold Martian winter, falling back as ice rather than forming a stable hydrological cycle. Energy released by nuclear detonations cannot replace the missing greenhouse gases or provide a permanent solution. Mars is too cold, too small, and too geologically inert for such brute force tactics to create lasting planetary change. Mars also lacks the internal dynamics Earth has. Plate tectonics, volcanism, and mantle convection are critical to Earth's ability to recycle carbon, produce oxygen indirectly via photosynthesis-driven processes, and maintain long-term climate stability. Mars's geology is largely static. Olympus Mons, the largest volcano in the solar system, is ancient and mostly inactive. Tectonic activity is negligible. Without internal geological processes, there is no mechanism to naturally replenish an artificially thickened atmosphere, stabilize surface temperatures, or recycle nutrients for biological systems. Even if humans could pump massive amounts of gases into the air and generate temporary warmth, these effects would vanish over geological timescales. The planet's fundamental lack of dynamism is not something technology can overcome in centuries or millennia. It is a planetary law. Finally, consider the timescales involved. The minimum time for meaningful planetary transformation is not decades, not centuries. It is tens of thousands to hundreds of thousands of years, even with theoretical technologies that do not yet exist. We cannot accelerate planetary cooling, we cannot restart a magnetic dynamo, and we cannot create massive greenhouse gas reservoirs in a way that persists against solar erosion. Mars is, in essence, a dead planet with a thin, leaky atmosphere and no internal energy to sustain life-supporting cycles. Any terraforming attempt would be temporary at best, and for the first human generations trying to survive, it would offer no practical benefit whatsoever. Terraforming Mars is a fundamental impossibility under known physics and biology. The atmosphere is far too thin. The planet has no magnetic shield. Nuclear interventions cannot create lasting change. The geology is static, and the timescales required far exceed the span of human civilization. Every suggestion that we can turn Mars green relies on ignoring these hard planetary limits. Unlike the psychological or engineering challenges of colonization, terraforming is not negotiable. The laws of physics are absolute. Mars will remain cold, thin, irradiated, and biologically hostile. Any human presence on the surface will have to contend with that reality, not the comforting illusions of sci-fi or wishful thinking. Mars may be a target for exploration, settlement, or temporary research outposts, but the idea of reshaping it into an Earth-like planet remains firmly in the realm of imagination. The hard truth is that Mars cannot support self-sustaining human life without massive, continuous intervention. And even then, the planet's fundamental limitations, its thin atmosphere, lack of magnetic field, dead geology, and extreme radiation environment, make survival an ongoing struggle. Terraforming is not science, it is a dream, one that collapses under the weight of physics the moment you leave fiction behind. The red planet does not bend to desire, ingenuity, or determination. It is a world defined by limits, and those limits are absolute, unyielding, and unforgiving. Why underground cities don't solve it. At first glance, underground cities seem like a perfect solution to Mars's hostile surface. Burrow beneath the crust, and suddenly, radiation is blocked, dust storms are irrelevant, and temperatures stabilize. It's a seductive idea, a sprawling network of tunnels and domes, filled with life, protected from the relentless assault of the Martian environment. But as with every proposed solution for life on Mars, the truth is far harsher. The deeper you look, the more obvious it becomes that subterranean living is not a solution. It is a temporary, fragile compromise that ultimately fails against the same biological limits that plague surface colonies. Radiation, the most lethal invisible threat on Mars, is reduced underground, but it is not eliminated. High-energy cosmic rays, solar particle events, and secondary neutrons can penetrate meters of rock and regolith. Even in the thickest underground habitats, astronauts are still exposed to cumulative doses that exceed safe limits over years. Shielding cannot be made infinitely thick. Mass is a limiting factor in construction, and every metre of additional rock adds exponentially to the difficulty of excavation, transportation, and structural support. Radiation continues to damage DNA, neurons, and stem cells. Neurodegeneration, immune suppression, and hormonal decline. Effects that cannot be trained away or psychologically mitigated remain ongoing threats. Underground living may reduce exposure slightly, but it does nothing to stop the biological countdown clock ticking inside every colonist's body. Gravity, the silent killer, is another problem underground habitats cannot fix. Mars's gravity is only 38% of Earth's. No amount of rock or reinforced tunnels can replicate Earth gravity. Muscles weaken, bones lose density, cardiovascular systems shrink, and organs fail to maintain their Earth-adapted functions. Artificial gravity solutions, such as rotating habitats or centrifuges, are theoretically possible, but they are mechanically complex, energy-intensive, and difficult to scale for large populations. The size of an underground city needed to house even a modest community would make artificial gravity systems impractical, and partial gravity continues to degrade human physiology over years, creating cumulative damage that compounds across every bodily system. Gravity remains an unyielding biological limitation, even if the walls around you are hundreds of meters thick. Social and medical collapse are often overlooked in underground colony proposals, yet they are critical vulnerabilities. Human communities require functional healthcare, nutrition, social cohesion, and psychological engagement to survive. Underground habitats are inherently isolated, confined, and logistically brittle. Any minor failure in medical systems, nutrient delivery, or life support is magnified when access to the surface is limited. A leak in a water or oxygen line, a contamination event, or a system breakdown could become catastrophic, with repair options severely constrained. Social cohesion is harder to maintain in confined artificial spaces over years or decades. Small conflicts, boredom, and stress, while survivable individually, interact with biological deterioration in ways that amplify risks. A weak immune system or compromised cardiovascular function turns minor accidents or infections into potentially fatal events. Perhaps the most overlooked problem is the maintenance burden of underground cities. Every metre of tunnel, every habitat module, every life support system requires constant upkeep. Systems degrade over time. Pumps fail, air circulation falters, water recycling becomes inefficient, and structural stresses accumulate. As the population grows, the demand for maintenance grows faster than the population can realistically supply labour. Resources are limited, equipment ages, and every failure increases the risk to human health. Unlike Earth, where spare parts, industrial infrastructure, and professional repair crews are abundant, Mars forces colonists to rely on finite supplies and self-repair, often under extreme environmental constraints. Over decades, the maintenance demands of an underground city begin to outpace its ability to sustain life, making collapse statistically inevitable. Food, water, and air remain critical issues underground, just as they do on the surface. Hydroponic and bioregenerative systems are sensitive, fragile, and nutrient limited. Water recycling, already challenging on the surface, becomes even more precarious underground, where storage and filtration systems are confined and repairs are difficult. Oxygen generation and CO2 scrubbing require continuous energy input, specialised maintenance and careful monitoring. A single failure can render sections of the habitat uninhabitable. Underground habitats may feel safe, insulated from dust storms or solar flares, but the biological requirements of humans do not change simply because you hide beneath the ground. Life support systems are temporary lifelines, not permanent solutions. Underground cities on Mars are a trap disguised as safety. They mitigate some immediate environmental hazards, but they cannot solve the fundamental biological challenges of human survival. Radiation continues to damage cells, gravity continues to weaken the body, and closed systems eventually fail. Social cohesion and medical infrastructure are fragile under long-term isolation. Maintenance burdens grow exponentially, quietly eroding the colony's ability to sustain life. A community that appears secure and functional may be on a slow trajectory toward collapse, undermined by the very systems meant to protect it. The seductive appeal of subterranean life, protection, stability, and concealment obscures the unyielding truth. Mars is a biologically hostile world, and hiding underground does not alter the rules. Biology is not negotiable. Radiation, microgravity, immune suppression, hormonal failure, and multi-system degradation continue regardless of where humans live. A colony buried beneath the surface may survive longer than one exposed to Martian storms, but survival is temporary, fragile, and ultimately unsustainable for generations. Human reproduction, the final wall. If radiation, gravity, dust, and atmosphere have not convinced you of Mars' lethal reality, human reproduction is where the argument becomes absolute. It is the point at which biology draws an unbreakable line. On Earth, life continues because reproduction is possible, gametes are viable, pregnancies can progress safely, and newborns develop in environments tuned for human physiology. Mars, however, offers none of these guarantees. The conditions on the red planet are not just challenging, they are fundamentally incompatible with sustaining human life across generations. No amount of engineering, training, or technology can bypass this barrier. Once we consider reproduction, the discussion ceases to be speculative. It becomes scientifically irreversible. Radiation is the first and most immediate problem. Mars's surface exposes humans to ionizing cosmic rays and high-energy solar particles at levels roughly 40 to 50 times higher than on Earth. These particles do not just threaten adult tissues, they directly attack gametes, the very cells that make new life possible. Sperm and oocytes are exceptionally sensitive to DNA damage. A single strand break in a gamete can produce mutations that compromise the viability of an embryo. On Mars, cumulative radiation ensures that the proportion of damaged gametes rises steadily over months and years. Even under habitat shielding, secondary radiation penetrates walls and equipment, making total protection impossible. Unlike adult radiation effects, which may manifest slowly, damage to gametes affects the very foundation of human reproduction before conception even occurs. Radiation-induced damage does not stop at visible mutations. Modern biology has revealed the crucial role of epigenetic regulation, the chemical modifications that control gene expression across generations. Radiation can alter these epigenetic markers in ways that disrupt development, metabolism, and long-term health. These changes are not always obvious at birth. They may manifest as chronic illness, organ malformation, cognitive deficits, or predisposition to disease later in life. Mars does not just increase the probability of mutations, it creates an environment in which every generation faces compounding genetic and epigenetic stress, exponentially increasing the likelihood of developmental failure. pregnancy itself becomes a life-threatening gamble. Successful gestation relies on carefully regulated hormonal cycles, stable cardiovascular function, oxygen-rich blood flow, and gravity-adapted organ positioning. On Mars, partial gravity, radiation, and nutrient limitations all combine to disrupt these delicate systems. The uterus and placenta may function inadequately in low gravity. Fetal circulation may fail to develop properly, and nutrient transport may be insufficient to support growth. Animal studies in microgravity suggest that developing embryos experience organ malformations, delayed bone formation, and neurological abnormalities. There is no evidence to suggest that these effects improve in partial gravity, and the addition of Martian radiation and environmental stresses likely magnifies the risk. Each pregnancy becomes a high-probability experiment in failure. Even if conception occurs and gestation is technically achieved, developmental failure probabilities remain high. Organs may develop in the wrong orientation, bones may fail to mineralize, and the cardiovascular system may not function under reduced gravity. Neurological development is particularly vulnerable to radiation, which can compromise synapse formation, neural connectivity, and cognitive potential. The result is that children born on Mars, even if they survive infancy, are likely to experience severe long-term health challenges. The very process of creating a second generation, one that could continue human life on Mars, is statistically improbable. This leads to the ultimate conclusion. No healthy second generation can be guaranteed on Mars. The first generation of humans may survive for a limited period with artificial life support, shielding, and nutrient supplementation. But survival is meaningless if those humans cannot reproduce safely. Biology does not compromise. If gametes are damaged, if epigenetic patterns are disrupted, if pregnancies fail or produce non-viable offspring, the colony cannot extend beyond the initial settlers. Multi-generational survival is the scientific measure of habitability, and by this standard, Mars fails completely. It is not a question of engineering ingenuity or mental resilience. It is a question of irreversible biological limits, and Mars exceeds them. The implications are profound. Discussions of terraforming, underground habitats, hydroponic farms, or psychological support pale in comparison to this final wall. Even if radiation shielding were perfect, gravity were corrected, nutrients optimized, and dust eliminated, human reproduction would remain fundamentally compromised. Biology demands specific conditions for reproduction, conditions that Mars does not and cannot provide. Without the ability to produce a healthy second generation, any human presence is inherently temporary and unsustainable, no matter how advanced or resourceful the colonists. In effect, human reproduction is the ultimate arbiter of Mars's habitability. Radiation, low gravity, nutrient limitations, environmental toxicity, and immune challenges all converge in this single, irreversible problem. It is here that scientific optimism collapses and hope for self-sustaining life becomes untenable. The laws of physics, chemistry, and biology intersect in a way that leaves no room for compromise. Mars may host temporary human missions, but it cannot host a human civilization. Human reproduction is the point of no return. Every other obstacle, radiation, dust, water scarcity, gravity, represents a challenge that could, in theory, be mitigated, delayed, or partially solved with technology. Reproduction is different. It is not a problem to be engineered, trained, or compensated for. It is a hard biological wall, an unscalable limit that defines the red planet as fundamentally uninhabitable for humans. Once we accept this reality, every other discussion, terraforming underground cities, artificial habitats, loses its grounding in practicality. Mars is not just difficult, it is intrinsically incapable of sustaining life beyond a single generation. The final truth is unavoidable. For humans to survive, reproduce, and establish a continuous presence on Mars, the planet itself would have to change in ways that physics and biology make impossible. Until and unless such changes occur, changes that currently exist only in science fiction, Mars remains a world that can be visited, studied, and briefly inhabited, but never permanently colonized. Reproduction is the ultimate test of life, and on Mars, humans fail it before the first second generation is even conceived. What scientists actually agree on. When you dig into the research, the picture becomes clearer than any press release or public announcement will admit. Internally, NASA knows the stakes, and their risk assessments are meticulous, extensive, and uncompromising. Astronaut career radiation limits, long-duration microgravity studies, life support, stress simulations, and planetary protection protocols all converge on a single truth: Mars is fundamentally hostile to humans over the long term. NASA internal risk reports repeatedly highlight the unavoidable biological constraints we've discussed: radiation exposure exceeding safe limits within months, gravity-related musculoskeletal deterioration, immune system collapse, and reproductive failure. Every scenario assumes heavy shielding, artificial habitats, and optimized life support. Yet even in the best-case projections, multi-generational survival remains impossible. These documents are not alarmist. They are sober, methodical, and based on decades of human physiology, spaceflight, and planetary science data. The European Space Agency echoes the same conclusions. ESA's studies on long-duration orbital missions and planetary analog environments emphasize that the risks of radiation, low gravity, and environmental isolation are not theoretical. They are measurable, cumulative, and irreversible. Their internal position papers outline the stark limitations of human biology in extraterrestrial environments, cautioning that Mars will always exceed human physiological tolerance unless every aspect of the environment is artificially controlled. Public statements from ESA, like NASA, are often more optimistic, emphasizing exploration and inspiration rather than the cold, biological realities that dominate their internal risk modeling. Academic consensus aligns with these positions. Published research and peer-reviewed papers reiterating that no human can survive on Mars indefinitely without continuous support from Earth. The language is careful, precise, and cautious. Biologically unsustainable. Multi-generational impossibility. Limits beyond human adaptability. Across agencies and universities, the message is unanimous. The only difference between public perception and scientific reality is presentation. Optimism sells tickets and headlines. Consensus sells facts. If humans are biologically constrained, robots are not. Artificial explorers thrive on Mars in ways that humans never could. They do not require oxygen, cannot suffer from radiation-induced DNA damage, and have no need for gravity-adapted musculature or circulatory systems. Dust storms, atmospheric thinness, extreme cold, and toxic perchlorates are trivial for a robotic system engineered for resilience. Rover wheels crush regolith, sensors penetrate the soil, and instruments measure chemistry without consequence. ASA does not need a breathable atmosphere or a stable pressure environment. It does not risk cancer or organ failure from radiation. What humans cannot endure for months, robots can endure for decades. Curiosity, perseverance, and their successors are proof that Mars is not a dead planet for science. It is simply a robotic science planet, not a human one. All the discoveries, all the soil chemistry, all the geological insights, these are possible without a single human stepping foot permanently on the surface. Robots can explore, map, and even conduct experiments in conditions that would instantly kill an unprotected human, proving that Mars is valuable for science even if it is biologically incompatible with us. This is not failure, it is strategic adaptation. Science does not require a human body to survive. By shifting the focus from human colonization to robotic exploration, Mars becomes a treasure trove rather than a threat. Instruments do not age biologically, do not need life support, and do not face multi-generational challenges. AI, drones, and rovers can operate continuously, transmit data across millions of kilometres, and return precise scientific measurements that inform our understanding of planetary formation, climate history, and astrobiology. Humans can guide them remotely, design experiments, and even experiment with limited interventions on the surface, but survival is irrelevant for robots. They succeed precisely because they are biologically neutral, unaffected by the very constraints that render Mars uninhabitable for humans. Mars's biological barriers do not spell the end of space exploration. They redefine it. The distinction is critical. Survival is impossible on Mars itself, but access, research, and human participation from controlled environments are not. Lunar habitats, orbital stations, and artificial gravity modules allow humans to participate in space without exposing biology to extremes that Mars enforces. The Moon offers lower radiation exposure, minimal gravity adaptation over short durations, and closer proximity to Earth, making life support and emergency evacuation feasible. Orbital habitats can simulate gravity, control atmospheres, and create stable ecosystems that allow human physiology to function properly. This is the blueprint for sustainable human presence. Bring Earth with you, rather than trying to adapt humans to Mars. Humans can visit Mars, study it, and even conduct complex experiments. But habitation, colonization, and multi-generational life are biologically forbidden. The laws of physics and biology do not say "not yet" or "we need better tech." They say unequivocally that Mars is incompatible with human survival over the long term. We can explore, innovate, and learn, but any permanent human presence requires Earth to be the foundation. Life support systems, gravity simulation, controlled habitats, and closed-loop ecosystems are the only environments in which humans can survive off-world. Mars is a laboratory, not a home, a destination for science, not for civilization. The science is clear. Human ingenuity cannot override planetary biology.